but didn't shout recording at us. makes me nervous. There we go. Okay. All right. So we had started or kicked off last week with single sample T. Okay. And remember, single sample T is a situation where you have a sample and you're wanting to compare against some either population value or some reference, right? Some reference value. You're saying that the population value for this, or sort of the value in the population for wherever I've sampled is some value, and we're going to go through and test against that. We don't see these too often, but they do come up. So just wanting you to sort of understand. Here, my null model is that my population value, my population mean, is equal to something, right? This is often some sort of reference value, but it can be actually anything, any value you want to set, right? You're just saying this is consistent with, or my best guess for what the population value is under the null model, okay? So we went through and gone through and talked about stuff there. And then we jumped into our independent sample test. Independent samples test, again, is the workhorse of psychological science, right? Any means-based thing that we do is probably going to break down eventually into an independent sample t-test, okay? And here what we're doing is we've drawn from two samples with unknown population values, right? And what we want to do is say, are these did I draw these samples from populations with equal means, okay? And so again, null model is the difference between population mean 1, population mean 2 is equal to 0. My alternative model is that the difference between population 1 and population 2 is some value that's not 0. Okay, so a non-directional hypothesis, right? And again, we're just saying that our point value here is 0. Anytime we're looking at some null model, it's almost always that something is equal to 0. Okay. So we went through and talked about some of our assumptions here, looked at our formula, right? And the thing here is we've got the sort of difference in sample means over the standard error, the difference in sample means, okay? The issue with the difference in our standard error here versus our single sample test is our single sample test, Jack, how many sources of error do we have to worry about in our single sample test? Just the one, right? When we go through, we're working on an independent sample test. Now we're working with two sources of error. We have to go through and account for both of those. So what we see when we're calculating our standard error is we've got variability that you expect with sample 1 and variability we expect attributable sample 2, and we got to add those together. Okay. And Finn, what does this then do to our standard error for our independent sample test relative to our single sample test? It makes it bigger, right? There's more fuzz in there because I got multiple sources of error to go through and to account for. Okay. Then we went through and talked about kind of how this works, right? That we can go through in any two distributions. I could have feasibly, although unlikely, get a sample that has a massive benefit for one of the population relative to the other. Simultaneously, you get samples that sort of suggest a massive improvement for the other population versus the other, right? So we need to go through and take both of these into account when we're calculating our standard error. And then we talked about situations where we have different sample sizes, right? If sample sizes are pretty similar, it's not too much of a deal. But if we've got situations where we have wildly different samples, experimental folks, for you, if you're going to controlled randomized stuff, probably won't run into this a ton, right? Just because you've determined who's in what group. For clinical folks, this will become a huge issue because you're often looking at pre-existing stuff, right? And the pre-existing stuff for the general population versus sort of the specific population you're looking at is quite discrepant. So we can figure out how do we go through and address this, right? Now, the assumption under our test is that the variability in the two populations that I'm pulling from is identical, right? So from a theoretical standpoint, it doesn't really matter who you pull from because the variances should be identical across the populations. Problem is, from a practical standpoint, they're not going to be the same number, right? And the sample with the larger number of observations, Catherine, is going to be more or less representative or more or less precise. More precise, right? So again, if I'm saying population 1 and population 2 have equal variance, right? But I've got 60 people from population 1 and 20 people from population 2, which one of those samples should weigh more into the estimate of the true population variance, population 1, right? And so this is where we get into our pooled variance. You're going to be using pooled variance a whole lot, right? This is just saying that what we're going to do is we're going to weight the variance of the larger sample heavier in coming up with our sort of composite variance estimate than the other one, okay? And so here what we're doing is we're taking sample size from sample 1 minus 1 multiplied by the variance, sample 2 multiplied minus 1 multiplied by the variance over sample size 1 plus sample size 2 minus 2, okay? Look me in the eyes. When you're doing this, make sure that you're using variance and not standard deviations. Okay, mathematically, the pooled standard deviation, if you were to plug standard deviation estimates into that and then run a pooled standard deviation, it's going to be a different value than if you're using variances. Okay, always work with variances and then take the square root of that to get to your standard deviation. Okay, if you don't do that, you're going to be off, right? So just make sure that you're working with variances when you're running your calculations and then work backwards to get them to standard deviations. So your final formula here for your independent sample t-test is going to be the difference in your sample means over your pooled variance estimate divided by your number of people in sample 1 plus your pooled estimate over your number of people in standard in sample 2, and then you take the square root of that. Okay. So Jayla, is this number and this number going to be different than one another? Nope, it's the same, right? This is your pooled variance. Your pooled variance is your guess for what the true population variance is across within these for these two groups. And the assumption is it's the same, right? So you're not worried about one being different than the other because the assumption is they're identical, right? This is just your best accurate estimate weighing out the differences in your sample sizes. People generally kind of following the logic of how we're constructing the test up to this point. Okay. So then also just thinking about in general, degrees of freedom can be something that we don't sort of pay attention to a whole lot, but we should, because it's going to give you information about how people conducted their analyses. And if we see degrees of freedom that are jumping around in ways we wouldn't expect, it just means that people are using different subsets of the full sample. That's kind of an important thing to know if they haven't sort of informed you. And then Scooby-Doo, so we got to go to Halloween and stuff like that. We're excited there. Okay. All right. That was sort of the catch up to where we were last time. People understand the difference between our single sample tests and our independent sample tests. Okay. All right. So what we now need to start thinking about is effect sizes. Okay. And remember, effect sizes is going to be our way of looking at magnitude of effect in the population or estimate of magnitude effect in the population, independent of sample size. Okay. Remember, with my inferential tests, I'm basically testing that some value is sort of equal to 0 to a billion decimal places. And if I get enough people in my sample, Jayla, am I going to eventually find that those things aren't exactly equal to 0 to a billion decimal places? Yeah, right. So again, the argument is if you're running hypothesis tests, your p-value is just a measure of how many people you have, right? If I get enough people, I'm going to have a really small p-value. Okay. Our effect size, on the other hand, is telling us how much of a difference or how much of a relation we're actually seeing in the data. Okay. And again, there's a number of different ways to do this. With our single sample T, we had our actual estimate, right? And then we also had some standardized measures. Same thing here, it just gets a little bit more complicated with your independent sample T test. Now, one way we can go through and do things is we can look at raw difference. And again, I'm going to pick on you just because your lab study is something that we can all see and have a good conceptual understanding of. We're looking at like mass or weight or things along those lines. That's something we understand. If you tell me that you're working with sort of an adult male who weighs 80 pounds, that's small, right? If we're working with an adult male who weighs 300 pounds, that's very big. I have a good conceptual understanding of that, what it looks like. If I say people are 50 pounds, there's a difference in 50 pounds between this group and that group. That's a lot. If there's a difference between 2 pounds between this group and that, I know what that means, right? And so raw difference can be a nice intuitive metric of effect size if we're working with things that sort of make some sort of normal sense, okay? Same thing, Jayla, if you're working with looking at in your lab civil suits, right? And so there's some difference across trials and you're looking at dollar amounts in terms of awards and things along those lines. People understand dollars. I can tell you whether or not that's a sort of a difference that I think is meaningful and interesting versus not, right? This is where raw difference can be a really effective metric of effect size. But for most of us, we're dealing with make-believe constructs, with make-believe scales that don't have any sort of intrinsic meaning to them, right? And this is where it starts to help become to have a standardized metric for effect size. And Cohen's D for our independent sample t-test is going to be just the mean of your first sample minus the mean of your second sample over a standard deviation estimate. Okay? And remember what Cohen's D gives us, it's basically, you can interpret this as kind of like a z-score. It's giving you a metric of difference in standard deviation. Okay. The problem is with our independent sample t, what do we use for that standard deviation estimate? Because we've got a couple, right? Now, Cohen would say, from a theoretical perspective, it doesn't matter what standard deviation estimates you use because population standard deviations are assumed to be identical. So just pick one, it doesn't matter. Okay. What's the practical problem with that? What do you think, Glenn?
So it doesn't matter. So Cohen's saying it doesn't matter what standard deviation you choose because it should be the same. Where my mind jumps to is like during a research study, you're not necessarily sampling the population. So like the standard deviations could be quite different between samples.
And if I'm thinking about my effect size, which one might I be? Which sample standard deviation might I be motivated to use?
The smaller one.
The smaller one. Why?
Well, the smaller one is going to give you a smaller fraction, so it's a larger effect size.
Cohen would say it doesn't matter. Population, you're assuming that the population variance is going to be equal, so it doesn't matter which one you use. But from a practical standpoint, I'm going to be tempted to just pick the smaller one because it can give me a bigger effect size, right? And so what we need to do is think carefully about what we're using as our standardizer. And this is going to be the issue consistently across these problems within your own work. I'm going to go through and I'm going to create a reported metric of effect size. What do I use as my standardizer? Okay. And what we want to do is be very thoughtful and have a good reason. You want to be able to defend, if I'm reviewing your paper, why you chose the standardizer you did. And there are different scenarios where you might choose different. Okay, this is another reason why effect sizes have taken a while to really catch on, is because it's requiring you to think and not just have a computer program spit stuff out at you, and people don't like that. But this is what we should be doing all the time to be able to say, this is what I use to calculate my effect size, and this is why. Okay. So some options here. One option is what we can call, and so note that across literatures, and you'll find this, and this is another thing that makes this really difficult, not everybody is using the same symbols in the same terms to talk about everything, right? So you got to be really careful with this, right? But by convention, one thing we might calculate here is a Glasses delta, okay? Glasses delta is just going to be sample mean 1 minus sample mean 2 over the standard deviation of some control group, okay? If, let's say, Jack, you're doing some work looking at sort of different sort of models of psychopathology against some hypernormal group that has sort of nothing at all, right? There's no history of sort of mental health concerns or something like that. And you're looking at mean differences. Maybe you go through and say, you know what, the people who have no sort of mental health concerns, this is my control group, right? And so what I'm going to do is I'm going to put this metric in terms of variability we see among individuals without notable mental health difficulties, right? You can make an argument that this is my control group. Now, if you've got a group of hypernormal people who have never had any anxiety or depression ever over the course of their life, I would argue that's maybe not a sort of normal sample, right? That's actually kind of atypical in its own way, but you could make that argument. Okay, Kate, sort of different if you got an experimental study that you're running, and you go through and you have here people who are just getting sort of responding to something having watched like a neutral film, like just sort of not, we didn't mess with them. We're just kind of getting kind of where things are at. And then a comparison group where they had some sort of manipulation that kind of changes something. And then you go through and look at the outcomes, right? In this case, if this is just, you have one group that is just the state of existence in the world without sort of fooling around with anything, you might say, this is my control group and this is the group to have. And what I'm going to do is I'm going to go through and I'm going to look at sort of differences in sort of these groups with respect to variability that we would just expect out in nature without screwing around with anything. And same thing, clinical folks, if you were going through and running like some sort of treatment study, you have sort of this group that is just kind of your weightless control, and this is your group that got treatment. You might run glasses delta and just say, we're looking at differences across these groups relative to a variability that we would just see if people didn't get any help at all. Okay. So an option here. Questions about glasses delta? And one we might want to go through and use this as a metric. Basically, if you have a really nice, clear control group, glasses delta is awesome because I can talk about things in terms of variability just as they exist out in the world if we weren't messing with anything. But sometimes we're going to have comparisons where we don't have a clean control group, right? Jack, you might be looking at sort of people with sort of this type of sort of psychopathology versus this type of psychopathology. There's no real one group that should serve as the basis for comparison because they're fundamentally different, right? So it would be hard to say use glasses delta for something, right? Or Jayla, let's say you have looking at sort of people's responses of perceptions of guilt with sort of this novel manipulation in terms of jury instructions, this novel manipulation of jury. There's no real control. So glasses delta starts to become hard because there's conceptually no real strong comparison group. In this case, what we might do is we might calculate something that we call by convention Hedges G. Okay. And Hedges G is just going to be, we're using our variance estimate or the square of our pool variance estimate as our standardizer. Just take that pool variance estimate you calculated for your test, take the square root of that, that's your pool standard deviation, and then you're just kind of taking the weighted average across these. Okay. Again, if I don't assume that there's sort of huge differences across here, we're just kind of taking an average and running with that. Careful. SPSS will tell you it's calculated Cohen's D. I don't know what Cohen's D is. Cohen's D isn't actually a thing. It's just, I mean, it is. It's just Cohen doesn't specify what to use as your standardizer. So if you just tell me you calculated Cohen's D, I don't know what you mean. You have to tell me what the standardizer is, right? We'd say Hedges G, but some places will use the pooled standard deviation and not call it Hedges G. They'll call it Cohen's D. You just got to be careful and to look carefully at how they're going through and calculating this stuff. All right. Other thing that happens now, particularly with Hedges G and experimental folks, is you've sort of done a better job of recognizing this and accounting for this. We go back through and look at sort of research from the 40s and 50s and 60s and 70s and stuff like that, where we're using really, really small sample stuff, experimental types of designs. What you can find is studies that give you very, very large effect sizes if you were to go through and take a look at this. The problem is they're impossible to replicate, right? Which is counterintuitive because if it was an effect that big, someone else should be able to find it. Problem is what we know, if we have very small samples, it biases our effect size, right? If I have very, very small samples, what happens is my estimate effect size is way bigger than what it should be in the population, okay? And so if you sort of look at sort of this graph, this is plotting your effect size here along your degrees of freedom, right? And so you can see now this is, if you have 10 degrees of freedom for a paired sample test, that means you had 12 people, 6 people per group, right? And what you see is something that's notably higher in terms of your effect size than what you would have if you have 50 degrees of freedom, okay? So what we can do to counter small sample bias is we can go through and calculate what is sometimes known as Hedges unbiased G, okay? Calculating Hedges unbiased G is pretty straightforward. You just go through and calculate G like you normally would, and then you just multiply it by a correction, okay? And that correction is going to be 1 minus 3 over 4 plus the degrees of freedom of your test here, -1. Okay. And Charlotte, as sort of your sample size gets bigger and bigger and bigger and bigger and bigger, what does this do to your correction here?
It's gonna get smaller.
It's gonna get smaller and smaller and smaller, right? So I'm taking 1 minus a very, very small number, which is essentially multiplying this by 1, which gives me something about that I would guess here, right? But if I've got really small numbers, right? Now I've got, this is a larger number, take 1 minus a larger number, which is giving me a smaller decimal. If I just multiply something by a smaller decimal, it's gonna drive things down, right? And so if you've got a situation where you've got possible concerns for inflation of your effect sizes due to small samples, what we can do is we can calculate hedges on bias G, and that just attaches a correction to this. Now the question is, how small do my samples have to be before I sort of start to implement unbiased G? I don't know. It's really up to you to think about it. If it's something that you're concerned about, then you can go through, and there's going to be obviously cases, you know, if you've got, you know, 9 or 10 people per group, then this is an obvious one. If you've got 20 to 30 people per group, probably not going to make a difference. If you're worried about what that inflation looks like, calculate G, then calculate unbiased G, and then just look at the difference if it's anything sort of worth sort of meaningful and worth being worried about, then you can go the conservative route or whatever. Again, what we're going to do is we're going to go through in this next problem set, have you in Excel go through and just put together calculators so that you can just drop in sort of all the information you want and just calculate it for you. It's much better. It's quicker. It's easier. You don't have to remember each time you go through and we want to do this. How do I go through and calculate unbiased G? It also reduce the potential for like calculation errors and stuff like that. It's a pretty slick thing, right? But just wanting to think conceptually, should I apply a correction given sort of the size of my samples? And then sort of just want to make a defense for that. Questions about this? Cool. Other thing you can do from secondary analysis, you can go through and calculate effect sizes there. I want you to use these, right? But if you're reading a paper and all they give you is t-tests, right? That's cool. I can get approximation of D with that. Here's a different sort of version of this. This is super, super nice if you got papers where the authors haven't calculated effect size and they haven't given you means and standard deviations. This will happen. You can go through and sort of reverse engineer stuff, and that starts to become super helpful. And again, up here, small, D equal 0.2, medium, D equal 0.5, large, and D equal 0.8. Those are benchmarks that he said don't use as sort of like rules from heaven. And people did that immediately. So just be careful with some of those interpretations.
On the first for secondary analysis,
Yeah.
on the right of the square root, is that supposed to be n1 times n2?
Yeah. But probably this should just be, I mean, 2 times your t-test divided by the degrees of freedom of your t-test is probably the easier way to go through. All right. Okay, so run through an example. We're going to say researchers are interested in school performance and students having viewed Sesame Street's children, those who did. Scholastic performance of 10 high school students having reviewed Sesame Street in childhood compared to 10 students who have not. Students having watched the program had a mean age of 93 with variance of 22.2. Those with no exposure had a mean grade of 85 with a variance of 17.8. Okay. So what we want to do again with all these problems, null model, null and alternative model using symbols, 95% confidence interval for the difference in scholastic performance, index of the absolute magnitude of the difference in these samples. What are we looking at for there? It's our effect size, right? Our hypothesis tests, our S values, our Bayes factor, and then pulling things together in a full interpretation. Am I just like standing in front of like the good screen right in front of you?
It's like I have put up on the computer.
Okay.
now, so.
All right. So, going through and sort of working through this, interval estimate, math is pretty straightforward here, okay? Here's for our first group, no Sesame Street and mean variance, Sesame Street and mean variance. What we need to do first, even though we technically don't need to, because we've got equal sample sizes, but we're just gonna, just to walk you through kind of the pooled variance, calculated pooled variance. So we're gonna have, in the sample size for sample one minus one times your variance, sample size two minus one for your variance over sample size one, sample size two minus two. So we've got 9 times 22.2 plus 9 times 17.8. Denominator here gives you a pooled variance of 20. Okay. Also, if I take 17.8 and 22.2, I average those two, what do I get? 20, right? So you don't need to go through, you didn't need to use this for this particular problem. I just walked you through so you can see how to go through and do it. But generally, this is almost always how you can go through and do things, because rarely do we have samples that are sort of identical. But okay, here's our variance estimate. Our pooled variance is going to be 20. And go for our standard error, the difference. We're going to take our pooled variance over the first sample, pooled variance over the second sample, go through and do that. We got 20 over 10 plus 20 over 10 gives us a standard error, and then take the square root of that, gives us a standard error of 2. So then for our confidence bound, just taking the difference in these two groups, okay, plus or minus 2.101 times my standard error is 2. Where did I get 2.101? Yeah, Kevin.
Table.
Yep, that's your critical T, right? Here you've got 10, 10. So I've got degrees of freedom of 18. So if you go through and you look at your T table, find degrees of freedom of 18 with alpha 0.05, it's going to give you a critical value of 2.01. T tables are nice for these simple problems here. As you start to get into sort of more degrees of freedom and things along those lines, you're not going to be able to find some of that on a table. Just go online, go to a critical T value calculator. You just punch in your degrees of freedom, whether or not you have a 1 or 2 tail test, it'll give you critical value. So here is your critical value for this. You run this out, so we get a lower bound of 3.8, an upper bound of 12.2 for this particular study. Charlotte, give me an interpretation of this interval estimate here.
Like based on the data, it's plausible that the point estimate or the like actual difference between the two groups falls between 3.8 and 12.2.
Yeah, right. We're going through, we're looking at sort of grade point or GPA or sort of points on some sort of thing, right? And we're anywhere from a 3.8 advantage for the Sesame Street folks, anywhere up to a 12.2, right? And if we're thinking about sort of a 0 to 100 grade point grade level, or sort of or total test score 0 to 100, thoughts about the precision of that estimate?
It's a pretty big difference.
Big
There's a
difference,
pretty big
right?
range.
We're anywhere from like sort of like maybe a fraction, like a third of a grade point to over 1 grade sort of point, right? So it's pretty big, but again, we've got a total sample of 20 here, right? So we wouldn't expect that to be super precise. Questions about the calculations that we went through and ran here? All right, so for our effect sizes, we're just calculating a couple different ones here, right? Depending on how you wanted to do it, right? Here is just calculating Hedges G. My mean difference over my pooled standard deviation. The difference here, if I take pooled variance was 20, I take the square root of that, right? I get 4.472. It gives me my effect size here, which is really, really large. Okay. Eyes on me. Don't divide by your standard error. That's just gonna give you your T statistic there, okay? Make sure this is your pooled variant or the pooled standard deviation here, okay? So again, based on my estimate of Hedges G, I would say that my Sesame Street folks are outperforming my Sesame Street folks by about 1.8 standard deviations. Is that big? That's massive, right? That's absolute massive. Okay? But what I might also say is I know I only have 10 people per sample. There's no way that's representative or generalizable. And I know that that small of a sample is going to inflate my estimate of my effect size. So what I might do is I might say, okay, I'm going to calculate an unbiased G for this. Okay. An unbiased G is I'm just going to take my effect size here and multiply it out by my correction factor. So here it's 1 minus 3 over 4, 10 plus 10 minus 2 minus 1. I do that and my Hedges unbiased G is 1.7. So it's not a massive reduction, but it is sort of about 1/10 of a point reduction in terms of sort of accounting for the small samples here. Other thing I could do if I really wanted to say my no Sesame Street group is kind of my control. Like that's kind of the state of the world outside of educational programming, right? Is people sort of not exposed to Sesame Street. So I want to say thinking about Sesame Street as manipulation or intervention, like if I go through and apply that, what's the expected difference relative to just like people out in the world who are not exposed to this? I can conceptualize this as a class delta, which I mean, I think this would be a fine way to do that, right? Here I've got the difference in my mean, so my standard deviation of my control. Here I just take the standard deviation of my no Sesame Street group, and now I've got a value of 1.9, right? And close to 2 standard deviations difference, which is pretty wild. Okay. So again, any of these could be defensible, right? It's just up to you to go through and say, here's what I did, this is why I did, this is why I think it makes sense. And it's the best estimate for kind of what we're doing stuff. Questions? Yeah, Finn.
Would it ever make sense to just kind of calculate all three and then decide, or would that make you more prone to picking the bigger one?
I think probably what you should do is think about the problem first and think about like what makes the most sense. If you calculate all three, if I was gonna go through this, I would start to think that boy, that Hedges G starts to make a lot of sense to me, you know. So probably wanting to think before you jump into the calculations, what makes the most sense given the methodology, given the question and things along those lines, and say, okay, this is how I'm gonna go forward and do this. Probably of these, that's probably the most defensible, just given the size of the sample, right? And Sesame Street is kind of ubiquitous, right? It's all over the place. I don't know that there's sort of like a Sesame Street and a non-Sesame Street group. You throw Elmo up, kids are gonna know who Elmo is, right? So that's not to say they're watching tons of Sesame Street, but it's not like that Sesame Street naive individuals out in the universe, although you might, but those are gonna be different people for different reasons that sort of, you know, so probably this corrected effect size is gonna be your best bet for this one. Questions? All right. Null hypothesis test and supporting test, this is pretty easy at this point in time, right? Just the difference between your two groups over your standard error. You've already calculated all this stuff. Like by the time you get to your actual inference test, it's kind of old news. It's kind of a formality at this point in time, right? Do I already know whether or not I'm going to have evidence against the null? Yeah, you're nodding yes. How did I know that already? Charlotte?
Well, I would say because the confidence interval is above 0.
Yeah.
So
Zero, no difference between these groups is not a plausible value based on the confidence bound. Sorry, you know I'm gonna reject it on one, right? Be careful with this. When you're going through and you're interpreting your confidence bound, please don't tell me, well, we found evidence of an effect, P less than blah, 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 whatever. additional evidence for this effect is coming from our confidence valve that sort of did this or that. It's not additional evidence, it's the same evidence, right? Like you will never have a situation where your confidence bound gives you a different answer than your inferential test. It's the same stuff, right? So really, by the time we go through and calculate this confidence interval, there's not really new information to be had with my inferential test because it's just going to tell me I'll get a p-value, and that p-value will allow me to calculate an S and a BFB, and it's giving me a metric of sort of the extent to which my data are compatible with the null model. So if you really want to get sort of like deep into that, but in terms of decisions, it's already give me far more information than I get with the p-value anyway. So again, by the time I get here, I already knew I was going to violate the null or sort of have evidence against the null model. Here, my p-value is very small with this, right? And particularly with a really small sample, that's kind of impressive just because I'm wildly underpowered. It's just that, at least based on the data that I've got, we're seeing a massive, probably unrealistic effect that we could contribute to Sesame Street, right? So, but if we go through and we do this, here we're calculating my S value, which gives me a S value of 10. Here's my base factor, about 64.5. Just going through and calculating these up, okay? These will start to become more difficult to calculate, particularly in SPSS. If you got like p equals 0.00 or p less than 0.001, and you double click on that, it's a decimal like this. This is where those Excel calculators start to become critical because they just cut, paste, and drop it in there for the proper value of that. All right. So results of our Sesame Street example here. Okay. For our null model, we're saying the mean grade of high school students exposed to Sesame Street, high school students not exposed to Sesame Street is equal across their respective populations. Okay. Again, notice here, and please make sure that you're doing this. I'm not just saying there's no difference between these populations. I'm actually like specifying what these populations are. What are we actually looking at, right? Mean grade, right? So again, sort of packing that in there to force us to think carefully about what are we doing, what are we testing, and who are we trying to generalize this to? Okay. In statistical notation, here's my null model, my alternative model, my confidence interval, my effect size. Here, I've gone through and calculated all three. Don't calculate all three for me. Calculate one and just tell me why you calculated one. Okay, you got to choose. Here we've got our test statistic, our critical value, our test statistic, our p-value, and this is my p-value written in scientific notation. And by convention, we're reporting three decimals. This is below that, right? Here I'm just providing, following Wilkinson, providing precise p-values in just a different notation. People understand scientific notation, sort of have brushed up remembering how kind of that stuff works. Okay, just make sure you do, because this is what I'll be looking for. Okay, please don't give me a p-value like to 16 decimals. just do this. This will be faster and easier. Okay. All right, here's my S value. Okay, I've got an S value of 10. They say results of the independent sample t-test provide similar evidence against equivalent performance in these populations as would observing 10 successive heads and tosses of a hypothesized variable. Okay. Here's the thing. I don't give you templates. There's just only so many ways to say this unless you come up with a better way to go through and say it, right? That's awesome. Play around with it. But if this is the way you want to go through and talk about that, that's awesome. Go through and do that, but make sure that we're just not saying sort of the similar evidence against the null. Tell me what the alternative is. Tell me what the null is. Work that into it so I can understand that you understand, or that I know that you understand what we're doing with this stuff. Okay. For my base factor, 64.5 here. Based on the available data, the likelihood of greater academic performance among Sesame Street exposed high school students versus non-Sesame Street exposed students is at most 64.49 times that of equal academic performance. Okay. Base factor, you can play around with this a little bit. There are different ways to go through and sort of pitch this, right? If you go back through and look at sort of slide on sort of interpreting this. There are different ways to go through and do this, so play around. If you have questions about your interpretations, come see me. I'll kind of help you square away with that. All right. Then we've got our summary here, right? We've got high school students reporting exposure to Sesame Street in childhood, demonstrated an 8-point increase in average grade as compared to high school students with no prior exposure to the program. Okay. The difference observed with these data is consistent with the 1.7 standard deviation increase in performance relative to students with no Sesame Street exposure. Okay. What I'm doing here is I'm telling you how much of a difference are we seeing? And this starts to become really important, right? We're saying estimates of the population difference compatible with these data range from 3.8 to 12.2 percentage points. Despite the small sample available for the study, results of an independent sample t-test provide relatively strong evidence of greater academic performance in students exposed to Sesame Street childhood, right? T, P, S, base factor, just kind of listing all those out, okay? Here, what I'm doing, I'm going through telling you how precise. Here, talking about evidence against the null. Okay. Although methodology of the study requires additional scrutiny, the current data suggests that early exposure to educational programming could be associated with 2/5 to over a full letter grade increase in average exam scores. Okay. Where did I get this piece of things? Where did I get 2/5 to over a full letter grade increase in average scores? Yeah, the confidence interval, right? So my low bound here is about 2/5 of a point. 4 points is about 2/5 of the letter grade. Here is over a full letter grade, right? Is this a standard way to go through and sort of interpret things? I don't know. It's just if I'm looking at that interval estimate, thinking about how big of a magnitude is this, I'm just saying, well, on the low end, it could be this much, on the high end, it could be this much, right? A different way of kind of presenting basically an effect size, try and convey some sort of practical importance of this. Okay. Now, obviously, there are lots and lots and lots and lots of other things that start to come into play about some kids exposed to educational programming, things along those lines. Are we seeing a letter grade increase because a student watched Sesame Street versus that? Not, probably not, right? But this is what we're seeing, at least in a direct difference across these two groups, at least with the data that we've collected. So again, sort of in your interpretation, you want to make sure that you're getting all these elements together, right? Talking about magnitude, we're talking about precision, we're talking about evidence against the null, we're talking about practical effects. This is all way, way better and more interesting and informative. Just saying, yeah, we found a significant difference across groups. That's sad, it makes me bored, right? It doesn't actually say anything about what we've done, okay? There's just so much more we can extract and should be extracted from these tests outside of just identifying p-values, yes or no, is above 0.05. Because if that's all we're going to do, then you don't have to write up a results section, because I've got eyes in my head and I know what numbers mean to determine where you're a benchmark and where you're not. This is you and your opportunity as a researcher to really try and drive home to your audience what it is, what we found, why it's important, what the practical impacts are. Questions on this? All right. So up to this point, we've talked about running through our independent sample t-test in situations where our variance estimates, we're assuming that they're equal across populations, okay? Problem is, what happens if they're not? What happens, Jack, if you go through and you've collected data and you're finding based on your sample data, variability in one group is very much different than variability that you're seeing in the other group, right? If we're assuming that the samples you've drawn are representative of the population, sometimes we're going to see differences that are sort of large enough to start to suggest that maybe the population variances aren't the same. Maybe they are different. What do we do with that? How do we go through and deal with it? Okay. This starts to become a problem because our standard T distribution, or the family of T distributions, right? All the sort of the nice sort of things that we've gone through and tabled, those sampling distributions assume equal distribution or equal variances across my two populations. If I violate that, what happens is those t-tests that I'm seeing tabled are no longer accurate representations of the actual sampling distribution of sort of the samples that I've pulled in. Okay. I'm not going to pop up another paranormal distribution slide, but I could if I would have wanted to pull the trigger. You don't even know when it's going to happen. But that's essentially what we're doing. We're running a test based on an assumed distribution that's not actually fitting our model, right? We've got a violation of our fundamental assumptions, right? Now all of a sudden we're comparing sort of one team with 11 men on the field and another one with 14, right? If we assume that both teams have 11 people on the field at all times, we can't actually make the same interpretations because we've got a fundamental violation of the rules. Okay. So what do we do with this? Okay. And so what we do when we have unequal variances, what we got is we have a new distribution, we'll call it T prime. Okay. And because we don't know what the distribution of T prime is, it starts to reduce our confidence in the accuracy of our results. Okay. So a couple of different things. This is not a new problem. We've been working on this for a while. Old school, if you go back sort of in our sort of history, right? So there's a solution, Variance-Fisher table. Variance-Fisher went through and tabled distributions, various distributions of T prime, but it's pretty limited to a specific number of distributions. It didn't cover like all possible scenarios that you could run into. So cool if your data kind of fell along those things, but if it didn't, not super useful. Okay. And so what we use now, so anytime you go through and you look at a sort of output from a statistical program and that has unequal variant or equal variances not assumed, what it's probably doing, and this is what SPSS is doing, is giving you a what we call Welch-Satterthwaite solution to this. Okay. And the assumption underlying Welch-Satterthwaite is that we've got a T prime that does follow a legitimate pattern in the T family. We just don't know what the distribution or what the degrees of freedom is. Okay. So let's say, Cindy, that you have a T test with 38 degrees of freedom, right? And if you had equal variances across your evidence of equal variances across your two populations, you would just look in your T table under 38 degrees of freedom, and that's the sampling distribution that we would be working from, right? And we would get our critical values and things along those lines. Problem is, if we violate this, you don't have any of the unequal variances. Welch-Satterthwaite is saying that the distribution of your test is somewhere in that table. We just don't know what value it is, right? We don't, because when we violate assumptions, we still have a T distribution. We just don't, the T distribution we have doesn't match up with the degrees of freedom that we would expect. And so what we have to do is we have to estimate the degrees of freedom as an approximation here, okay? And what we do is we go through, and I used to have people do this, and it was just an unnecessary math task. It's probably not useful, so I sort of pulled that out. But essentially what we're doing with this is estimating your degrees of freedom for your sampling distribution as a function of your variances and your sample sizes of each group. So what you'll do when you do this is you'll go through and you'll calculate the same test statistic as you would. You're just comparing it against a different critical T than what you would normally identify under your table. Okay. And then you get an associated p-value to test with that. Now, how do we go through and how do we test? How do we get evidence for differences in variances across the samples? Okay. Here, what we're generally going to go through and look at is our Levine's test. Now, Levine's test is not without its problems, but it's probably fine for most general things that we're doing. And what a Levine's test is doing is it's going to go through and it's going to replace each score in a sample with its deviation from the sample mean. Now, we can square that. It can be the absolute difference. It doesn't matter a ton, right? So if you're saying that you have, here's group one, here's group two, right? You've got 7, 8, 1, 3, 6, 5, 3, 7. And these are your data. This is the stuff that you're going through and comparing across these two groups. What your Levine's test is gonna do is it's gonna go through and calculate a deviation score for all of these, right? And it's gonna go through and calculate whatever the mean of your sample is. And then it's gonna calculate a deviation score 2, deviation score 3, so on and so forth. And then do the same thing over there, okay? And then what we're gonna do is we're just gonna go through and we're gonna conduct an independent sample t-test. Those two deviation scores, okay? And if the average deviation for the mean in your first group is about the same as the average deviation from the mean in your second group, what should you get with an independent sample t-test of those deviation scores? No difference, or they should be very close, right? But if this group starts to deviate a whole lot more, your deviation from the mean tends to be 5 or 6 points as opposed to 1 or 2 points. The average deviation score here is going to be much higher than the average deviation score there, and if it's big enough, trigger that independent sample t-test, then you're going to get a significant Levine's test with this. Okay. Yeah.
Is there like a measure, like of how much deviation, I guess, from each one that, or is it just a judgment thing?
Well, and here's the thing, it's not just a judgment thing. Let's go through. Let's say, just eyeball on this. So the average score here. Let's say the mean is 6. But let's say it is. Here the mean is. Okay. So here we're gonna be 1, and we'll just do absolute differences, 2, 3, 2, 3, 0, right? And here it's gonna be 2, 2, 0, 1, 4, 1, 2. Okay. If what we did, Charlotte, is if we went through and now just used these are data set, and then we just run an independent sample t-test across those. If the difference is big enough to be statistically significant, then you've got evidence for a Levine's, so evidence for a violation of homogeneity of variance.
Gotcha, thank you.
Okay, do people kind of see how this test is working out? Okay, but then this starts to become important, Charlotte. So we see we got a difference across these two, right? So we've got a difference, so let's call this an average of say 2, and this an average of right. But let's say so we've got 1, 2, 3, 4, 5. We got 5 people in the sample, 5 people in the sample. Are we likely to find a difference between the average of these two columns of numbers? No. What if we had 50 people? We had 100 people. Okay. Always remember that. So that anytime we're basing something on an inference test, it's largely just a measure of how many people we have, right? And then thinking about that, if I've got large sort of means-based samples, so you can say go back to sort of Jack, you're doing sort of big stuff on prolific, and you got like sort of massive differences across things. And let's see, I've got sort of say 600 people, 300 one group, 600 people in the other group. And let's say I got a Levine's test that's being flagged for giving me evidence of inequality of variance. Should I be super concerned about that? Probably not. Because the difference in my variances might be very trivial if I actually look at it. It's just kind of, I've got like a massive number of people in my sample. So of course it's gonna, anything that I test in a sample of 600 is probably gonna come up as significant. So I shouldn't immediately freak out and think I've got wild differences across my variance. Probably what I ought to do is actually look at the variance of this and look at the variance of this and saying like, are they really different? Or are they kind of sort of, so again, like anything else, this is what we'll use, and we'll always kind of base our stuff off of Levine's. There may be situations where like, yeah, I've got sort of evidence for violation of homogeneity of variance based on my Levine's test, but I also have massive samples. And so it probably doesn't mean anything too critically concerning. Probably just means my hypothesis test is telling me that I have a lot of people in my sample, which I already know because I collected the data, right? So always want anything carefully about not just basing decisions on whether or not something is significant or not, knowing kind of what good is going into this stuff. And so there may, and this will start to become more relevant when we get into ANOVA and think about how we're sort of breaking things down and pulling things apart. Because we have unequal variances, it starts to sort of change our calculus on how we go through what we do in some different procedures and things along those lines. So before we jump into something that's super complicated, let's take a beat, sort of say, is this something I need to be concerned about, or is this something that's probably just an artifact of the fact that I have just pretty large samples here. Okay. And we'll talk about this as we continue to go through examples in class. People comfortable with sort of Levine's test and sort of with Welch-Saderwhite solution, things like that. There are arguments, right? And so people as statisticians will make arguments that you should always just use Welch-Saderwhite, even if you don't have evidence of violation of homogeneity of variance. Here, I could have pretty substantial differences in my variability. But if I only have 5 people in my sample, am I likely to detect that with the Levine's test? Probably not. Doesn't mean it's not an issue, it just means I don't have enough people to detect sort of that difference. So even though I don't have evidence of it, so just default to Welch-Saderwhite anyway, right? And just always go through and look at the permitted tests, right? When you get into some SEM applications and things like that, prominent methodologists make, yeah, just always use the corrected test, because if you don't have any problems, it just defaults to what you would have had anyway, right? I don't want you to do that necessarily here. Do look at your Levine's test and sort of make your decisions from there, but it's just sort of a position sort of within the sort of methodological literature that's probably not unreachable. How am I feeling about this? Okay. All right. Cool. Huh? So let's think about what happens if we do have a violation of our assumptions, okay? Having you read an article, I think it's Bonner, that's going through and talking about what happens when we have violations of assumptions and sort of the robustness of means-based tests to sort of different types of violations, okay? What we find, at least based on that, there's sort of opposing opinions sort of more recently, but in general, thinking about sort of situations under which our means-based tests are robust to violations and which ones they're not, okay? Now, if I've got violations of homogeneity of variance, right? I have evidence that, so Jayla, you go, and this is sort of a situation that very much can happen in experimental situations, then in sort of clinical situations too. Let's say you got your 2 groups and you've got different manipulations. In one group, everything's pretty tight, so people's responses tend to be pretty similar. And with the other manipulation, people's responses are way all over the place. One, you've got a situation where your manipulations are doing fundamentally different things in terms of variability. You got one manipulation that's much cleaner. It tends to sort of get people in the same spot, versus another one, people kind of all over the board. That's kind of an important thing to know outside of your statistical test. But if you've gone through and you've got relatively equal sample sizes, your t-tests are probably pretty robust. So you don't have to worry too much about this. You want to use your Welch-Saderwhite correction, your unequal variance is assumed, but your t-test is probably going to be okay with this. Also, minimal impact of non-normality in our observed scores, assuming a reasonable n, and your distributions are reasonably shaped. Okay. Catherine, for our means-based test, do I have any specific assumptions about the distribution of my observed scores? No, I don't, right? My normality assumption refers to the distribution of sample means, right? And I know my distribution of sample means is going to start to become really normal once I have reasonably sized samples, or if whatever I'm sampling is coming from a normal distribution population, right? So again, a huge misconception about my means-based. Well, I went through and looked at my scores, and my scores were skewed, so therefore I did some wacky non-parametric nonsense. But no, your assumption isn't about your actual observed distribution, it's about the distribution of samples. So if you got nice sized samples, you don't have to worry about this too much, right? Unless you start to have distributions that are wildly dissimilar in their shape, right? So okay, let's say you're going through and doing something with Jared where you got some different manipulations about sort of or norms and honor and things along those lines, and you go through and have one group of people doing stuff and you're getting like a pretty intense rate skew on stuff. In your other group, you got a pretty intense negative skew the opposite direction. Again, that should immediately trigger you your screen and you start thinking about like, okay, something about this manipulation is something very different across these. And that's like an extra statistical thing. That's a conceptual thing when I think about like, what am I actually doing? And how is this making people behave in terms of their scores? But also right now, in terms of your sort of going through and running like just your straight up t-test, I might start to become concerned because with one group, your skew is going to pull those means high. In the other group, it's going to pull those means low. And what you could find is this massive difference between your two groups, but it's mostly just a function of opposite distributions pulling stuff the other way, opposite ways, right? Now, if they're all skewed positive, then it really doesn't matter. It's kind of evens it out. But if you got distributions that are very clearly pointing in different directions or wildly sort of different shapes, you might want to think about sort of whether or not your test is robust to that. Questions about this? Okay. So most situations, our t-tests are going to be pretty robust. Areas where you need to start worrying about stuff, if you have distribution, you observe different distributions or different shape, coupled with unequal variance, right? That starts to become problematic. Okay. Not only are my skews pointing opposite directions, I've got one group that has a much larger variability than the other. That's making it hard to know what's going on with this. This will really start to mess with your tests. Okay. If I've got unequal variances coupled with unequal sample sizes, okay, I've got one group that is much larger and one group is much smaller, and I also have evidence of differences in variability across these two populations. I can't have multiple, my t-test can't have multiple estimates of variance. It just has to have one variance estimate, which is my pool variance, because the test is assuming equal variances. But what happens if I have my sample that has more people, has larger variance? What's that going to do to my pooled test, my pooled variance? It's going to make it larger. It's going to estimate your overall variance for the full group as much larger than it maybe is for your smaller group, right? But because that pool variance, it's going to make it much larger. And if my variance is larger, William, what's that going to do to my standard error?
Makes it larger.
Make it larger. And what's that going to do to my t-test?
Makes the t value smaller.
Yeah, right. So I'm going to have a conservative test, right? Because the group with the larger variance is the group that is getting weighted more heavily in the pool variance. And so now what's going to happen is I'm going to have a test that's too conservative. I mean, it's going to be harder to identify a difference than it would be if I had equal samples and had that balanced out. Same thing if I have my larger sample with the smaller variance, right? Same thing. That group is going to go through and weigh more on the calculation of my pool variance. It's going to make that pool variance smaller than it should be. It's going to drive my t-test up, right? And it's going to mean that I'm going to identify differences when there aren't really differences to be through. So thinking about not only recognizing that unequal samples and unequal variances are problematic, also knowing what the impact that is on our test starts to become really important. Thinking through critically about what I found and how much faith I can put into stuff. Yeah. Similarly, if I have violations of normality and a small sample size, then that starts to become problematic. Again, we don't have assumptions about the distribution of observed scores. But if I've got small samples and like wild amounts of skew or things along those lines, it just makes those mean estimates much more susceptible to those values that are hanging out on the edge, right? And can start to drag stuff around. So again, you don't have to have a ton of people in there, right? But if you've got samples of 25, 30-ish for a means-based test, that's pretty good, right? For standard experimental work, if you can go through and put 25, 30 people in each cell, that's reasonable representation. And so it starts to make it reasonably robust to stuff, so long as you don't have like wild markers out there, and then you want to go through and identify those in screening and sort of do stuff. Questions about this? Okay, so what we're gonna do, so let's go through and take 10. What we'll do is we'll run through an SPSS example here, looking at marital satisfaction, social desirability. Pull up your handouts with that, and we'll walk through the handouts for the screening, answer the output, and kind of get kind of what this looks like in SPSS. Awesome. So, yeah, take 10, come back, a little after 3:30. Okay, questions to this point on, questions on, T-test stuff. People feeling okay. What is?
By minimizing that window, will like a little one pop up?
Ah, there we go. Thank you.
Yeah.
I've been teaching this question. God knows how many years. Can't figure this out.
Zoom is elusive.
Okay. All right. Feeling okay sort of with sort of the concept behind sort of our independent sample t-test, understanding considerations and things that we're working on with this. Okay, cool. All right, so we're gonna go through and do an actual data example here. So what we've got, we're saying investigators are interested in gender differences in marital satisfaction, motor vehicle accident survivors committed to long-term heterosexual relationships. 22 women and 5 men meeting diagnostic criteria for PTSD subsequent to motor vehicle trauma completed the Locke-Wallace Mental Adjustment Test. Scores range from 2 to 158, with higher values indicating greater relationship satisfaction. Christians also completed the Marlowe-Crown Social Desirability Scale to assess for differences in tendency towards socially desirable responding in male and female survivors. Okay, so the idea is that what we're really interested in is sort of differences in marital adjustment, but also want to say, like, are there differences in just social desirability responding within this example here? Okay. Based on previous research, investigators hypothesize that women will report greater levels of marital satisfaction than men. Tendency towards social desirability responding is expected to be similar across groups. Okay, so we're kind of laying out kind of what we expect within this. Okay, and then what we're going to do is all the stuff that we did before, kind of working through this. So in SPSS, this is pretty straightforward. When you actually get to the actual t-test that you're going to run, you just go to analyze, compare and a sample t-test. Will pop up a little window like this. You go through and you sort of put over your test variables, your dependent variables, what you want to test for. Down here, you put your grouping variable, hit define groups, and it'll tell you sort of like what values you're going through and comparing, right? Click estimate effect size, and then so you go through and set this up. Okay. What we want to do here is walk through quickly sort of our approach to screening with this. And again, this will be all laid out within the video you'll watch, but just want to make sure that people are kind of seeing kind of what's happening with this. So for our independent sample screening, the thing that you need to be careful with this, because you're working with 2 independent groups. Okay, and so when we're looking for distributions and we're looking at outliers and things along those lines, you want to make sure that you're looking at these groups separately. Okay, because you don't want to go through and sort of combine everybody, because a value that may seem to be pretty much okay within the overall combination of these 2 groups, if you're looking specifically among men or women, you may see something sort of way out there, right? So critical is that you, as you're working through this, that you're always going through splitting file, Again, we'll make a big point of that in the video, just make sure that you're going through and splitting things up so that you're looking at groups separately, okay? So this is what we're doing here with some of these initial commands. And then we're gonna go down through and we're gonna look at our descriptives for both men and women within this sample, okay? Jack, just looking at this output, is there anything that you're seeing that's overly concerning with either one of these groups based on this table here?
Female have what seems like a quite larger mean statistics than male.
A larger what?
Mean statistic.
Okay, so the means are higher, okay, for Lock Wallace, okay. And so sort of good to start going through and taking a look at this stage of screening, maybe starting to look at sort of whether or not things are pointing the direction that you would expect them to. So that's a good thing. What else at this stage of the game are we maybe sort of interested in looking at, William?
Well, for both Lock Wallace and the social desirability scale, males have a much higher standard deviation, which could partially be a factor of their sample size, but just something to be aware of when you start thinking about the types of analyses you want to run.
And so for some of those descriptive statistics, want to go through, take a look at mean standard deviations, kind of get a general sense for what's going on in your data. Here at this stage though, what we're really wanting to look at is sort of observations, making sure that the number of observations that you have in there map onto what you think is going on in your data set. And then also looking at your skew and your kurtosis, right? Are we seeing sort of problems in terms of skew kurtosis values? What do you think, Charlotte?
I think so. I'm not super familiar with like the actual like measurement of skewness, but it seems like the skew for females is like significantly higher than
Okay.
males, or lower rather. It's negative,
Well, yeah.
or it's more skewed.
Yeah, I got, I'm picking up what you're putting down there. Yeah. So again, what we're looking at, and so that's certainly true, right? So it looks like scores are a little bit distributed a little bit differently across these two groups. The main thing though is we're looking at absolute magnitude of skew, absolute magnitude of kurtosis here. General rule of thumb is sort of values below standard absolute value of 2, right? So here we've got some evidence of skew across both of our measures, but nothing here that would necessarily raise red flags for stuff, okay? Now for our kurtosis, we are seeing kurtosis levels exceeding absolute value of 2, particularly for our men, okay? But if we also go through and we take a look at some of our samples here, we got like a ridiculously small number in here, right? And we notice that sort of our kurtosis values are negative. What is a negative kurtotic distribution look like? Do you remember? What's the shape of negative kurtosis? William's conducting music back there.
So it's like flat.
Yeah, flat,
correct.
right? Flat, negative, yeah.
Platypus.
Yeah, platypus, yeah. Platycurtic is gonna be flat, right? Sort of these square distributions. If I've only got 5 observations, I got 5 people with different values, what's that graph gonna look like? Flat square, right? So certainly we would note that we've got sort of high values of negative kurtosis in this. It's probably direct in the fact that we don't have a real sample that we can do anything with, right? So probably what's happening. Okay. So again, we look at our sample size in this. So number 1 is what I'm gonna be focused on is like, I don't know if we have really, I mean, like, yeah, we can calculate a test, but this is sad, probably not worth doing in real life. And we also have a massive discrepancy in terms, well, not massive, but sort of a reasonable discrepancy in terms of sample size. Right, we've got we have 4 times the amount of women that we do sort of men in this sample, right? So all of a sudden we've got some stuff that's worth taking a look at and sort of keeping in the background. Yeah, Jayla.
So then, because you're saying for skewness, it's not a problem, but kurtosis it is. Kurtosis.
I'm not saying it's a problem, I'm saying it's notable, right? So again, and this is what we're doing when we're screening. Again, you've got your consultant hat on. You're just walking through, kind of making check boxes. You're like, huh, that's interesting. Want to go through and take a look at that? Huh, And as you go through and make sure to make a mark that I'm not determining anything is problematic yet. But what I would say is, boy, those samples have me concerned, right?
So the kurtosis just for male?
Yep,
or
just
also-
just for men. So for our women, this is kind of within that bounds. Again, rough guideline of about 2, right? And again, just because my skew and kurtosis is less than 2 doesn't mean that my data are normal or approximately normal. We just kind of use that as a general rule of thumb for talking about potential sort of notable violations of normality or problematic violations of normality. Okay. But again, do we have any assumptions of normality in our observed scores with an independent sample t-test? Nope. We assume that our distribution of sample means no. Now, is marital satisfaction in motor vehicle accident survivors in the population of male survivors, the population of female survivors, is that normally distributed? I don't know, right? It's hard to know. But I do start having concerns about my distribution of my sampling distribution here because I've only got 5 people in that sample. It's going to be hard for that to get normal if that's sort of wildly. Probably skew is worth more sort of being concerned about than the kurtosis, but it's still things I'm going to go through and know. Okay. So what we're going to do is now we're going to go through and run some pictures, right? So I'm going to go through and I'm going to get a histograms for Lock Wallace for histograms for my Lock Wallace, my marital satisfaction for men and women, and for my social desirability scores. Kate, what am I seeing for in my histograms for men?
It's pretty square.
Yeah, pretty square. Is a histogram useful with 5 people? Not really, right? So we would go through and note that for men in the sample, histograms are pretty square, but there's really not much to be able to, we just don't have enough representation or really get a good sense for what's happening with these. For women, we got more people. 21 is not huge, but we get those sort of maybe generated a histogram. Any questions about any observations about stuff that's going on there?
Book must be a little bit negatively skewed.
Yeah, we got some negative skew here, right? This maybe looks like marital satisfaction, like almost maybe we got like maybe a bimodal thing going on, right? So maybe something that I would go through and take a look at and think carefully about, like, do I have, is there something going on with this where I've actually kind of collapsed 2 different groups? What might be going on? And if we're measuring marital satisfaction, what might I have going on with my groups here? So again, remember these are women who have been involved in motor vehicle accidents with PTSD. Not that that's necessarily sort of relevant, but it's just kind of for sampling. Yeah, Finn.
I mean, I'm not sure this is what you're going for, but I'd wonder about treated versus untreated.
Maybe treated versus untreated, right? So if there are people who have treatment versus sort of no treatment, right? I just think maybe we've got people who are just categorically different in terms of like overall marital satisfaction, where people, you got folks in good relationships, and then maybe some folks who are not so good relationships. We know psychopathology can really impact relationship functioning, things along those lines. And so I don't know. It's hard to know what to make of this, given that we only have 21 people. SPSS is giving me something that looks kind of bimodal. If I were to run it in a different program, it might look completely different. That's one of the limitations of histograms, is how we've been in certain things can start to pop up. Also recognize that as humans, we're sort of trained to see patterns when maybe there aren't patterns there. So want to be careful in sort of making hard interpretations, but I might look at that and think to myself, wonder if you may be curious, right? And if I'm describing this, I might say something maybe looks a little bit bimodal in this, right? Okay. So we go down through and look at our box plots. Box plots are nice because they're just generally sort of more rule bound, right? Is there anything super interesting going on with these box plots? Okay. For marital satisfaction, the men are about as generic as you can get, right? Again, there's only 5 people there, so there's not sort of too much that can go wrong. Among women, sort of maybe looks like a little bit of negative skew, but not anything sort of substantial. For social desirability, again, for men, a little bit of negative skew, but hard to sort of see what's going on with that. Maybe a little bit of negative skew for women, but there's nothing too worrisome to go through, and sort of nothing that's throwing up red flags with this. All right, so now what we're gonna do finally, we're gonna go through and we're gonna run some Z scores to go through and look at potential extreme values within each one of our groups, okay? Remember that with this, what we're looking for, your means for your Z score should be exactly 0. Your standard deviation should be exactly 1. If your means and standard deviation don't look like this for your Z scores, you've done it wrong. You need to go back through and sort of make sure. And probably what's happening in the files, right? Do we need to worry about skew and kurtosis with this? No, it's going to be identical to your observed scores. You don't worry about that. What we're looking at here, your min and your max. Cindy, if you're looking at this, do you see any, are there any concerns with extreme scores within this set of data? No, doesn't look like it. On the low end, we have something that approaches 2 standard deviations below the mean. At the high end, well over 1, right? So there's nothing. So there's no concerns about people hanging out way out in the end that it's going to go through and mess with stuff. So going through it, this is sort of where we go through and kind of pull this all together, okay? And again, for the next set that you're going to do, this is your template. Like do this, don't do other things, right? Missing data, looks like we've got 1 case where we've got missing Lock Wallace and Marler Crown scores. For case number 132, tell me which group that's coming from, right? So we know. Looks like we've got sort of woman in our sample who's missing these values so that we know. Accuracy, plausibility, I'm going to go through, make sure that all values are within sort of what we would expect. So that's looking okay. We moved the 1 case with the missing value, so I've got 26 my reduced set. Okay. Distributions for men, talk about skew, kurtosis, describe the histogram, describe the box plot. Not much we can say there, just because they're 5 people, but we're just kind of giving a description of those. For the women, same thing, skew kurtosis for Marlowe Crown, histograms showing some negative skew, box plots, remarkable, nothing much happening there. Outliers, extreme values, so reporting that separately for men and women. All Z scores are less than an absolute value, negative 1.26 for men. Less than or equal to negative absolute value, Z score negative 1.29 for both. There's nothing to be concerned there. Homogeneity of variance. This is, you'll get this out of your, once we actually run the t-test. Okay, so that's not the screening piece of things. Pull that in after we run the test. When you run your t-test, that's when you get your Levine's test here. So then we get down into our recommendations, okay? So we're saying missing this was minimal, despite the small sample. Design noticeably unbalanced, so we're noting that sort of like we don't have equal sample sizes here. Strong negative kurtosis in males as a result of the limited sample. Levine's test suggests possible violation of homogeneity variance for social desirability, okay? And then what we want to do is kind of pull this together, right? This is where, as you as a consultant, this is where you're making your money, okay? Pulling this together, we're saying anomalies, the distribution of scores among male respondents, likely attributable to small sample, all the discrepancy in the number of men is noteworthy. They suggest possibility of unequal variances in social desirability across men and women, particularly given the limited power Levine's test and samples of 5 and 21. Basically, what we're going to find is Levine's test is kind of like on that marginal level. But again, remember that Levine's test is an inference test is just like anything else. If I'm getting anything even close with samples at this size, I'm not going to dismiss it as like, oh, where it's like it's something I probably want to take into account or at least note. Analysis mean comparisons But proceed with caution, recognizing that these data will likely underestimate variability in marital satisfaction and social desirability, particularly among male survivors. Why am I saying that?
Smaller.
Yeah, because I've got 5 people, right? I certainly don't have the extreme ends of social desirability or marital satisfaction, and all male survivors of motor vehicle accident with PTSD because I've got 5 people in there, right? Um, recommend analysis of differences in social desirability, also used to correct for tests for possible violations of homogeneity variance. So just saying like more marginal, probably just use corrections to be safe, even if it's sort of bumping up against statistically significant with these sample sizes. Might as well just be safe. Correct. Or at least that's what we're writing. Questions about how we go through and tie this all together? Yeah, Jalen.
With Levine's test, that was like hand calculated or it's.
That's when we go through and we actually run the t-test or the actual t-test, it'll come up in that. So we're just sort of pulling that from something we have not yet done. And then sort of the last piece, want to have generalizability, okay? And you're not always going to have a ton of information sort of available with this, but we want to go through and think about like, what are the implications based on the information I have, right? We say generalizability marital satisfaction scores occur in set limited primarily by the inordinately small sample. I don't have enough people to generalize to much anything in this, right? Sampling strategy and participant characteristics are unknown. Samples of these size are unlikely to be representative of accident survivors in long-term heterosexual relationships, even on our own conditions, right? I mean, sort of, do we know sort of demographics or background characteristics of people in the sample? We don't. Does it really matter? Not really, because we've only got like sort of the samples were so small, it doesn't make sense to like our generalizability is really limited, right? You're probably not going to get this published just because you know probably don't have enough to work with this. And so certainly, yes, that other stuff would be great to know, but it's probably not relevant because of the limitations in that like 5 men and 21 women. It's unless I have a very compelling reason for why my samples are that small, it's going to be hard to sort of pull anything meaningful from this. Questions about how we sort of kind of go through and tie this piece of things together? Cool. So let's go through then and look at the actual tests. This is the thing. Screening takes forever. The actual test is pretty straightforward. You just kind of pop it in and sort of it pops out, and so it's pretty easy. Here we're just going to go through and run our independent sample t-test. And when we do this, we're getting our means or descriptive statistics here. This squares with what we found in our screening, right? 5 men, 21 women, same across both. Here's our means, standard deviations. So feeling okay with that. Then we go down through, we look at our tables for our independent sample t-test. Okay. Jack, what am I seeing for Locke-Wallace total on it? Let's start with Levine's test. What is the p-value for Levine's test telling me with this?
For equal variance assumed, it is less than 0.05.
Okay, actually here, hold up, sort of take a beat real quick. For my Levine's test for this F right here, what is this? Tell me, do I have concerns about violations of homogeneity of variance with this? No, exactly right. Why don't I have concerns about violations of homogeneity of variance?
Because the equals variances are assumed. Or
Well, so here we got equal variance is assumed, equal variance is not assumed. But for your Levine's test, this is just the test for both. This Levine's test is kind of the deciding point on whether or not I'm reading sort of this line or this other line. Okay. William, you shook your head, said we don't have concerns about violations of homogeneity of variance. You're correct. How do I know that?
Cause isn't it like for that, if that is less than 0.05, you're violating the homogeneity?
Yeah, exactly. This is the tricky thing with your Levine's test. This is a test where you're hoping for a large p-value, right? Because if I have a small p-value, remember anytime I'm testing sort of differences or having a p-value on anything, is probably testing whether or not something is different than zero. And in this case, I'm hoping that the difference between my variances is functionally zero, right? So in this case, I've got a p-value of 0.569. Now I've got pretty small sample, so there's limited stuff that we can infer from this, but at least based on this test, it's giving me no reason to be concerned that I have differences in variability across marital satisfaction scores across men and women in this sample, right? So there's no reason to go through and be concerned with this. So because of that, because I don't have, at least based on my Levine's, evidence for or concern for violation of homogeneity of variance, then Jack, you're correct. Then I would go to equal variances assumed and start reading this line up here. Okay, and if I do that, now take it away, Jack. So what is my inference test telling us?
I mean, the sig two-tailed is 0.033,
Yeah,
which is less than or equal to our 0.5, which is.
So by conventional standards, we would go through and reject the null and sort of based on that p-value, right? But if I go down through this table a little bit farther, here's my mean difference. Here's my standard error of the difference, and then here's my confidence bound. Like SPSS just went through and calculated what we would do by hand anyway, okay? And Kate, can you give me an interpretation of this confidence bound here?
Yeah, so based on our data, the point estimate scores for difference are compatible with approximately like negative 54.8 and negative 2.45. However, well, given our small sample size, though, this isn't a very precise confidence interval.
Wide. At least it seems wide, right? We know sort of up here, we know that our Lock Wallace scores range from 2 to 158, right? Which is random arbitrary values, right? But it looks like we could, based on these data, we could just go through, and this is another thing you gotta want to be careful. So these are negative. Now, does that negative, does that sort of sign mean anything really? Ben, you're shaking your head, no, why's that?
I mean, I get the sense that it just means, not that there was like an error, but it's like too broad to be interpretable, like it doesn't.
Well, maybe, and sort of, you might say that sort of like the interval estimate is way too big to sort of be practically meaningful, and that's sort of certainly something that you could do. But if we're just looking at, so I'm noticing this is negative 54 and negative 2.5. Is that sort of something to pay attention to?
So we're comparing against the female group, right?
Yeah, and that's really the thing.
Okay.
It's a math thing. It's like who did SPSS plug in there first? Men were coded 1 and women were coded 2, or men were 0 and 1 or something like that. So it just took 80 minus 108. And so what you want to do is just make sure sort of the sign on this really doesn't matter, so long as you understand who's outperforming who, right? And if we look back up to the mean, saying that women are averaging higher than men, and this is just saying that so you could phrase this as, based on our data, sort of men are reporting, our data would support differences across men and women, anywhere from men scoring about 55 points lower in marital satisfaction to as little as 2.5 points, right? Or you could just drop the sort of these and say, given that our hypotheses were that women would score higher than men, just say, sort of consistent with hypotheses, our data would support estimates, population differences in greater satisfaction for women, anywhere from about 55 points higher to 2.5 points higher, right? This is all arbitrary. This is just sort of the math. Just, you want to know what these values mean relative to what your actual sort of mean differences are, so that you can give proper interpretations. Okay. Now, if this was completely flipped and men were reporting higher levels of marital satisfaction than women. And that was the opposite of what we had hypothesized. That would be something for sure to cue in on. That, yeah, we're finding an effect, but it's in the opposite direction of what we had hypothesized. You think about what we're doing with that, right? So again, what we're seeing is, so based on our sample data, about a 28.6 point difference across men and women for reported marital satisfaction. But our data would support population differences anywhere from something pretty trivial, probably 2.5 point difference advantage for women, anywhere to about a 55, which is probably pretty substantial. We will see how we're going through and interpreting this, right? And based on this interval estimate, Kate, do we already know that we've have evidence to reject the null? Yeah, because there's zeros not in there, right? It doesn't cover zero, so we already know what's going to happen. All right, so let's go down through. And Cindy, tell me what's going on with Marlowe Crown here. First of all, let's take a look at our Levine's test. What's my Levine's test telling me? Right here.
Okay.
I'm a little confused on how we're reading this.
What's that?
I'm a little confused on how to read it. And like,
On how what?
on how to read it and how we're reading it too. So-
Yeah. So we've got a p-value right here, 0.054. So what does that suggest with our Levine's test? Do we have evidence for a problem or not a problem? What do you think, Kate?
Say, it's approach evidence for a problem, and given the small sample size, might wanna play it safe.
Yeah, I think that would be probably my approach, right? Is to say, and sort of watch this people navigate for that sort of trending towards. Hard to tell, is that trending towards or trending away, right? It could be moving sort of which direction, but I would agree, it's in the vicinity. Is 0.054 categorically different than 0.049? No, it's the exact same, right? Not the exact same, but it's functionally close enough, right? And so given the small sample size and the fact that this is gonna be underpowered, probably not something to dismiss back, oh, we're good, so there are no problems with concerns of violations of homogeneity of variance. I'm big, there might be, right? And if I look at these standard deviations, I got a standard deviation of, if I square this 16 for women and about 49. 45, so whatever 6.8 is squared. Yeah, I mean, they're different, right? And so what I might do is say, I'm just based on this, I might play it safe and just drop down to equal variance is not assumed, okay? And if you were to go through and make that determination in your problem set, cool, just let me know. Don't just automatically just go through talking about this or interpreting this line. Tell me why you dropped down to that, right? Because technically, you're sort of not over your threshold, but I agree it might be worth just saying like, just went through and read this. Okay. Now, if we go through and we take a look at this, Cindy, if we move over to looking at your actual t-test, do we have clear evidence for differences in social desirability across men and women in this set? What's that? Let's take a look. Let me just at first, how about this? Let's skip the p-value and just go to your confidence bound, right? What's your low bound for your confidence interval for the difference across men and women? Yep, negative 8.56. And what's your upper bound? What falls directly in the middle of those, the two estimates, right? So, yeah, I mean, like we've got literally almost sort of equal on either side. We've got p-values of 0.913. Our differences here, our point estimate of our differences, quarter of a point, right? There's nothing here to sort of go through and speak of, right? So at the end of the day, Kate, doesn't really matter whether we're using equal variances or not assumed. greatly, right? There's very clearly nothing to see sort of based on the data we've collected. Now, does that mean that there's no differences in social desirability in sort of men and women involved in motor vehicle accidents? No, it's just saying based on these data, we don't have enough evidence to say it does, right? So we would talk about this saying failing to find evidence for differences in. Yeah, Jack.
Yeah, I'm still struggling on the Levine's test.
Yeah.
For equality, specifically, what is our threshold that we're looking for? Is it that 0.05 or?
Generally, it's 0.05,
Yeah.
right? You know, and that would be traditionally, if I go through and I see my p-value here is less than 0.05, I would say, oh, I've got evidence for violation of homogeneity variance. And if that was the case, then I would look at equal variance as not assumed. Okay.
And then also, so we're looking for like a higher significance because we want to be further away from zero.
Yeah.
Because we standardized it to.
Yeah.
Okay.
And so what we're looking for is, again, remember, and this is why I kind of went through sort of Levine's test and what it's actually doing, is because if I don't have really any evidence of violation of homogeneity variance, I should very much be squarely in kind of null region, right?
Yeah.
Now if I start to get sort of close to the edge, it's saying I'm starting to get differences in there, which is problematic for my test, right? Which would then tip down. But so what I really want you to be thinking about is all of this is just based on an inference test. And if we know what the limitations of inference tests are, we can start to become more nuanced and probably responsible in terms of how we're going through and sort of interpreting things. So here, is this equal to less than 0.05? No, it's not, but it's close. And I know that this is a wildly underpowered test. And if I actually absolute difference in my variances, it's substantial. So I might just go down through and sort of decide to, even though this isn't less than 0.05, I might decide to go across here, right? Now it doesn't matter because like there's nothing to see there, right? But if there was, so that's a decision I might want to make, right? Other thing too, if I went through and I found that this was really small, p less than 0.001 or something like that, but I've got 300 people in one group, 300 people in the other group, am I sort of freaking out because I have a sort of horrible violation of assumptions? Probably not. I would go back up and sort of square those, take a look at my variances, like they're actually similar. I mean, I'd probably still go through and interpret equal variance as not assumed, but it's my assumption is that the sample of that size is not going to make a difference. So you can kind of go through and make a determination about sort of this is what's going on. This is a problem. It's not a problem. This is how I know why it is, as opposed to just being sort of tied to rule bound stuff of like, oh, every time this happens, then I have to do that. Probably not, right?
So then as n would increase, we'd expect the significance to decrease.
So for Levine's test, yeah, probably as sample like any test, as sample sizes get bigger and bigger and bigger, the likelihood of getting a small p-value increases, right? So just recognizing that, sort of taking that into context and interpreting things. Yeah, Jayla.
Yeah, I don't know if I'm thinking about this wrong, but like if you are going with the equal variances is not assumed, is your confidence interval always gonna contain zero? Or
No. For this, so this is, you got a couple of different things here. This is your Levine's test, right? That's just saying, do I have evidence for differences in population variance, right? And then sort of based on to what you see here, then you decide, do I read the top column or the bottom column, right? This from the T over, this is all sort of independent of the Levine's test. It's just equal variance is not assumed is a corrected test, and sort of the top one is just your sort of regular sort of conventional test. Yeah. So here you'll see that sort of these intervals. Well, I mean, this is a good point though, right? I see what you're saying. So if you go equal variance is not assumed, you have p-value 0.033. If you go equal variance is not assumed, that substantially changes your p-value and your interpretation, right? So here it does make a difference, right? Because if I was going to go through and say, oh, I'm just always going to default to equal variance is not assumed, that gives me a different decision by quite a bit than this, right? So I would probably say like, well, variances actually look pretty close. And so this is kind of what I'm going to go with and sort of go through and interpret that. And that would be completely fine. There's no reason to shoot yourself in the foot by going through and assuming this, right? But with the correction, and again, why are we getting wild, sort of pretty substantial differences across these two? Because got a ridiculously small sample, right? Things start to get unstable. Same thing too with going through and Cindy, if you're working with sort of other people in terms of screening, you got really small samples in there, you'll notice that your values of skew and kurtosis in Stata are different than theirs. And that discrepancy will be much bigger if you're using really small samples. It's just because Stata uses a slightly different method of calculating skew and kurtosis. If you got lots of people, it's gonna be really close. If you don't, it will look a lot different. Don't worry about that. It's just in terms of how things are calculated. Okay. So again, large things get weird with small samples. So you just gotta recognize that and sort of notice, know that the limitations of those small sample sizes. Okay with this? Yeah.
Go over again conceptually why having like a super large sample size also can kind of inflate and have you like violate the Levine's test or equal variance.
What's that now?
Can you explain again conceptually why having a really large sample can also make your value significant, so then you're violating
Yeah. Because remember that anytime we're sort of going through and running an inferential test, it's literally testing whether or not something is actually zero. Okay. And so if I have a really small sample, let's see, I don't know this, and when we get into correlation, right? So let's say, okay, I have a correlation of 0.20. Is that a significant correlation? What's that?
That depends.
It depends on what. Bro, what does it depend on? P-value. Well, the p-value is what I'm gonna try and to assess, right? To determine if it's statistically significant. What determines whether or not this is a significant correlation or not? 100%.
Isn't it like preset?
What's that?
Isn't it preset, like a certain like range is small, medium and large?
So yeah, and if we're like interpreting effect sizes and stuff like that, if I have n equals 20, is that going to be a significant correlation? What if I have n equals 75? Maybe, right? What if I have n equals 200? 100%. If I have n equals 5,000, yeah, absolutely. The p-value associated with that is going to be like infinitely small, right? The estimate of the correlation didn't change. It's the same, right? Our inference test is just telling us how much evidence we have against the null, right? Here with 20, yeah, I mean, is this encompass zero, the low end of that correlation, right? Maybe like negative 0.1, right? So it's to sort of 0.5, something like that, right? And so, yeah, no, a correlation of population value of zero is still reasonable, sort of given to the data that we've collected. But as we start to increase my sample size, what happens to that, to my confidence bound around R? It's smaller and smaller and smaller and smaller and smaller. So my sample gets larger and larger and larger. Zero gets farther and farther and farther away as a null value. Okay. It's still the same association, right? It's just I have sort of much stronger evidence, sort of basically irrefutable evidence at the sample size of 5,000 that the population correlation is probably zero, right? And so again, this is going back to the criticism of null hypothesis testing, that we're like doing some things, you know, are like really important with the null model or the null hypothesis testing. Basically, we're just saying, do you have a lot of people in your sample, right? There's probably, for the population correlation probably isn't exactly zero. It might be R equals 0.03, right? Is that a significant correlation? Probably not here, probably not here, probably not here. If we get to that, yeah, right. Your p-value doesn't, whether or not it's significant doesn't tell you anything about whether or not it's important. All it's just saying is this value likely zero, right? So, and again, this is the criticism of null hypothesis testing, is people argue reasonably, it's kind of a stupid endeavor Because the answer is probably never that it's exactly zero, if I carry it out, right? And if I just get enough people, it's always gonna be significant. So significance kind of loses its value as something that's reasonable or important or sort of interesting at all, right? That's where, so if we start looking at confidence bounds and effect sizes, then it starts to become sort of more important because you can go through and be like, oh, I have this significant correlation, big, well, that's not a correlation anybody cares about. Is it exactly zero? No. But just because you found it significant because you had some epi data with, 8,000 people in it, that means it's useful in practical and sort of important. Right? So the same thing with the Levine's test, right? My test is that whether or not to the difference or the variance across the difference in the variance across these these populations, which I've sampled, is exactly zero. So as my sample starts to get larger and larger and larger and larger and larger and larger, what will happen is even trivial deviations off of zero will start to trigger them as statistically significant. Same thing, this is why we don't go through and look at significance values for skew and kurtosis, because my sample gets bigger and bigger and bigger and bigger and bigger. Eventually, the test on whether my skew is exactly zero or my kurtosis is exactly zero, my data is going to say no, it's probably not exactly zero. But if my skew is 0.1, does that mean I have horrible violations? I have to completely redo like the type of no. So it's not a useful test, right? And the same thing with Levine, right? As my data gets sort of bigger and bigger and bigger and bigger and bigger, the likelihood of me detecting something that's probably not exactly zero starts to go up and up. So that doesn't mean I ignore it, but it's just sort of taking that into context and saying, at this point, so my sample is so powerful that I'm sort of starting to detect trivial differences and things. Same thing with your mean difference, right? If I got 5,000 people in both samples, like any sort of marginal sort of difference across those two is going to start to sort of get flagged as highly statistically significant. Doesn't mean it's useful. It just means that it's not exactly 0 to 7 decimal places. Yeah. So just always keeping that in your mind when we're interpreting statistics. Your null hypothesis test, your p-value is just saying like, it's giving you an index of the compatibility of the data with your null model. And if you've got lots and lots and lots of observations that says this thing is not exactly 0, that could be important. It might not be important. That's where you have to start thinking about method, what they're actually doing, and sort of practical implications. And that's where confidence bounds, the effect sizes start to become important because we can start talking about magnitude, right? Same thing in the opposite direction. I got a correlation of point, it's called 0.3, right? And let's say that's actually sort of nothing to sneeze at, right? That's a smallish effect size, right? But I've only got sort of 75 people in my sample. I got P like 0.055 or something like that. Does that mean that there's no correlation between these two variables? No, it just means that my best guess is it's about 0.3. My study's not powered to sort of identify 0.3. And so, yeah, I can't make a claim for an association between these two variables. Probably not going to say like nothing to see here. No one needs to sort of investigate this any further. Like it's so maybe worth looking with a larger sample and get a more precise estimate. So just adding sort of knowing what's going on in the nuts and bolts behind the scenes starts to become really, really important for making proper inferences from your data. Because people won't often do it in journals. They're like, no association here. Like, well, it's. Or sort of like this is what I love is so you go through and you're like, okay, so there's no difference between completers and non-completers in my study. Like, well, you only had 10 completers, and so that's yeah, just because you didn't find something that was different doesn't mean there wasn't any differences. It just means that you didn't have the power to only sample of 10 to really test the differences. And if I start looking at the demographics across people who did not complete, what I might see is something that starts to look concerning to me, irrespective of your null hypothesis test that you ran. So again, that's the big argument against null hypothesis testing. It's basically a test of how many people you have in your sample. If you have a lot of people in your sample, you already know that because you did the data collection, right? So wanting to be very careful and thoughtful in terms of how we're sort of going through and making our interpretations. Does that help?
Yeah, absolutely.
Okay, cool. Other questions about this? All right, cool. So last thing we're going to go through and take a look at here is going to be our effect sizes, okay? And so you just want to be careful in terms of how you're going through and requesting these. SPSS is going to give you Cohen's D, which isn't Cohen's D. It's what we had previously called hedges G, right? So again, wanting to go through and make sure that you know down here what's being used as the standardizer. And so SPSS is doing a good job of telling you what the standardizer is for each one of these, right? So here we got Cohen's D, we got hedges correction. Hedges correction is using sort of the correction factor and then glasses delta. Problem with glasses delta is you need to look at the standardizer and figure out which group is being used as the control group, because it might not be the one you want it to be, right? But that's just a cross-reference back up with your descriptives to see who's being used as the standardizer here. So here, hedges correction, probably your best bet. What it's giving you is point estimate and sort of confidence bounds for your effect size. Okay. And so here we're seeing about a standard deviation difference in marital satisfaction, right? This is a big fact, right? We're seeing that women are reporting, sort of based on these data, we're expecting women to report sort of higher, about a standard deviation higher in terms of scores of marital satisfaction relative to men. And that, so that's a notable thing. And this is even with the correction here, right? So, but what you'll see is you're looking at your confidence bounds here. Charlie, what's the low bound for my effect size?
For the lock Wallace edge.
Yeah,
Negative 2.07.
excuse me, yep, you're exactly right. What's the upper bound?
Oh, negative 0.8.
Negative 0.08. There's negative, like it's 8/100ths or 9/100ths of a standard deviation. Sort of anything that's meaningful or interesting, no. All the way up to over a 2 standard deviation change, right? So my confidence bound around my effect size is massive, so which is basically telling me I've got a good job for you to make somewhere between $1,000 a year and $10,000 a year, right? Could be anything from no thank you to absolutely, I'll jump on this right away. So just not much we're able to go through and say this. And then here, we don't need to worry about effect sizes for this thing because it was really cool. Oh. If we found something that was just kind of marginal, right? If we got like, so say if the p-value for this was 0.055 or something like that, I might want to go through and take a look at the effect size, given that we kind of had a marginal result. We know that we have an underpowered test, but here, like, it's very close to 0. So there's no need to or mess with that. All right. So if we go through and take a look, so you can go through and take a look. This is just me going through calculating effect sizes back in our history when I first started teaching this course. I was on my effect size crusade, so making people do all this, and so I made enough YouTube videos that I forced IBM to bend to my will and start including it as part of SPSS. So you no longer have to do these things necessarily because SPSS will do them for you, but you should still know how to go through and calculate effect sizes. So this is just giving you examples of how that would be done within this test. And so go through, make sure you take a look at that, understand how to calculate those by hand. Okay. So going through and writing this up, okay. Again, so this first piece, you don't necessarily need to have this in your write-up. I just think it's a nice way to kind of ground ourselves back to, like, what are we going through and looking at actually with this? We're saying independent sample t-test used to compare marital satisfaction, social desirability scores across male and female accident survivors diagnosed with PTSD. Null hypothesis tests. Null hypothesis testing in these analysis posits no difference in marital satisfaction or social desirability in the population of male and female survivors. Notice that when I'm up here, I'm talking a lot about, because this is all population level stuff, right? It's not about the dead, not about the sample. This is saying, like, out there in the universe, these groups differ, don't differ, things along these lines, okay? Here, going through and pulling it all together, say, evaluation, moral ground scores failed to provide strong evidence for differences in social desirability, desirable responding across men and women, okay? And so just going through and providing means, standard deviations, difference, confidence bound. Independent sample t-test identified and observed data is generally compatible with null or near null differences in these populations, given assumptions of the underlying model. Saying, like, just not much happening with this, right? So going through, and so there, we don't need to go through and say much more with this, okay? Results do, however, indicate potential for greater marital satisfaction. Female survivors with point estimates of unbiased G, suggesting a full standard deviation increase in scores among women as compared to men, okay? So here I'm starting out with the effect size. I'm saying, yes, there is a difference. It's about a full standard deviation based on our effect size that we can. Confidence bound, however, identified values ranging from 2.5 to 54.8. It's plausible estimates for the two difference in mean satisfaction across populations. It's worth noting that lower bound estimates supported by these data are likely not consistent with meaningful differences given the observed variability of the Lock-Wallace scores, right? So I don't know, and I don't expect you to know anything about the Lock-Wallace marital satisfaction scale, but you can just kind of look at sort of like the scores range from 0 to 150, something like that. I think one difference is probably not useful or meaningful in any sort of way, okay? Independent sample t-test also provides only modest evidence for an absolute difference in satisfaction in the larger population, right? So again, if I'm looking at my S and my base factor, right? Thinking about these as strength of evidence. Yes, I should have crossed the 0.05 line, but basically what this is saying is that evidence against the null model B is similar to that as getting 5 consecutive heads on a hypothesized fair coin, right? Jayla, if I go through and I get 5 consecutive heads in a coin that I'm telling you is fair, probably starting to be skeptical. Where you were willing to like bet the farm on the fact that that's a unfair coin? Probably not. Hopefully not. Hopefully not. Don't do that, right? Because that'll happen sort of on a situation where you will go through, right? So we say via base factor bound that these data suggest the likelihood of alternative hypotheses is at most 3.3 times that of no difference in satisfaction across female survivors. These odds correspond to a 26.3% chance of the null model being true under optimal circumstances, assuming prior probabilities of alternate and null is equally likely. This may just mean showing off and like sort of like giving you examples of different ways to go through and interpret sort of that base factor based on some stuff that we went through and talked about, right? This is just me trying to say like, yeah, we found something. But if we're being realistic and looking at strength of evidence, it's really not all that compelling. Okay. Small and unbalanced design. Sample further limits inferences that can be drawn from these results. Although data suggests possibility of greater marital satisfaction among females compared to male survivors, strong conclusions regarding magnitude, generalizability required further study. Right. So again, we're saying we found something. We need to be super, super cautious about what we're taking from this, right? This whole thing is highly suspect, right? I would not move forward with a whole research agenda based on this under any circumstances. It's saying that there's maybe not anything there, but I gotta be careful in terms of how I'm interpreting this and what I'm gonna do with it. We'll see how we're kind of sort of packing this together into something that makes some sense. And then here's, if you were to go through, write this up, the publication, don't do this because they'll probably, you run out of space with your pub and your reviewers will get mad at you. I will love it if it looks something like this. Here's maybe some ways that you go through and package this into. So, okay, here's like a results section. Here's the data screening. Here's what I found, right? It's larger than like I found a significant effect and not a significant effect for this, but it's arguably far more informative and useful for what you're writing up. Publication. Okay, questions? All right. Last thing we're going to talk about is repeated measures. Repeated measures are badass. These are designs that are going to go through and start to be a little bit more complicated, but super, super, super helpful in terms of sort of mapping onto a lot of the types of things that we're interested in looking at, and then also ways to dramatically increase the power of our tests. Okay, so when we're talking about a repeated measure design, we're looking at the same group of participants across one or more variables across 2 or more occasions. Okay, and I've got this asterisked. Okay, the reason is that with a traditional repeated measure design, we're almost always taking sort of this group of people that I have, and I'm measuring it right now, and I'm taking the same group of people, and I measure on a definite row, okay? The exception to this is if I have sort of an old school matched groups design. Okay, in that situation, right, what you would do is I would find all of you as my test group, and then I would find someone from sort of the general sort of random world who looks a lot like you, who looks a lot like you, who looks a lot like you on different sort of whatever variables I think are sort of important, right? So then you have you in the sample and then a doppelganger in the control group that are matched on sort of certain characteristics. Traditionally, what we would do then is use the data that we would get from that type of design in the same repeated measures framework here. Okay, you don't see a lot of match group designs these days. This was kind of something that was an artifact of some older methodologies, but technically, if you have match group designs, sort of you can sort of make arguments for looking at this in a repeated measures framework, which starts to become really, really advantageous in terms of power and things. So again, benefits of your repeated measure designs, these start to be just map on really well to a lot of the types of things that we want to take a look at, right? Jayla, if you're looking at some differences in, say, jury instructions or sort of like details of a case or something like that, have you look at a case with these details? And then have the same group of people look at a different case that's kind of similar with different details. And then see, do we see the same, do we see shifts in how people go through and approach things, right? If I'm sort of like doing treatment work, okay, look at you before treatment and I'll look at you after treatment, see if you've changed, right? I could go through and I could look at people who get treatment, people who don't get treatment, compare those two. That's a really messy way to go through and look at things, and I'm probably not going to get the level of detail I would get with a repeated design. Okay. Gives me more efficient use of resources, right? If I need to collect a group of people, now I only have to collect one group of people as opposed to two separate groups. Okay? And what I can do with this is really where you make your money, increased ability to count for and control for random error. Okay. Scores from the same individual measured on two different occasions in context, going to be far less variable than two individuals measured separately. Okay. So if I'm interested in so the impacts of having our class from 2 to 5 versus 8 to 11 in the morning, right? A far better way to conduct that study is to go through and have you all sort of take class at our usual time, have you measure whatever it is I want to measure, and then have you go through and have you take class from 8 in the morning to 11 in the morning, and then measure the same thing and see what kind of differences we get, right? What I could do is I could split you in half and have half of you go through and take the 8 to 11 class and have you the other half take it 2 to 5 class, but you're not all the same people, right? Like you're different, right? And sort of certain things. And are you an early riser?
I am.
You're an early riser. If Finn happens to be in the early riser field, Finn might say, "This is awesome. I love it to death." Right? Cindy, you've said that you're not an early riser.
No,
You'll probably
we were
not be
talking about
happy.
this.
So there's probably going to be differences across stuff. But if we have Cindy, you take it at 8 to 11, and then again at 2 to 5, Finn, you take it at 8 to 11, 2 to 5. What we're going to get is you all are acting as your same controls. We dramatically reduce variability due to individual differences and all other types of things that are going on, right? It's a much, much more powerful way to go through and test these types of things. And kind of our most basic approach to going through and doing this is going to be our paired sample test. And what we're doing is we're going to use our paired sample t-test to look at change in scores within the individuals across repeated measures. Circle this, star it to make sure you highlight it for your independent or for your paired sample t-test. What you're actually working with, your outcome is going to be your different scores. Okay. Different scores are the key thing that you're going to be looking at. Okay. You're going to have in your raw data set, you're going to have scores at time 1 and scores at time 2. I don't care about scores at time 1 and scores at time 2. What I'm going to do is I'm going to calculate the difference between time 1 and time 2. That vector of scores is what I'm looking at. That is the input for your this test are these different scores. Okay, that starts to become really important for screening, interpretation. I don't care about scores at time 1. I don't care about scores at time 2. And if they have wild distributions or whatever, it doesn't matter. The only thing I'm interested in with this is your difference scores. Yeah. So again, my null hypothesis with my paired sample test is that the mean of the difference scores in the population is equal to 0. Right? You take it at time 1, you take it at time 2, they're the same, doesn't matter. My alternate model is going to be the population difference score is some non-zero value, right? What we're going to do is we're going to go through and sample. What we're trying to infer is whether or not the difference score in the population, or sort of hypothetical population, would do this is going to be equal to 0. So the question we're asking here is whether or not difference scores across multiple assessments in our sample deviates sufficiently from D0 to start to conclude a non-zero difference in the population. Sample my data, and I go through the measure people at time 1, measure people at time 2. Do I expect my sample difference to be actually equal to 0 to 7 digits? No, right? What I'm just looking at is based on the sample that I have. Am I seeing enough deviation off of 0 for me to reasonably start to conclude or guess that probably the population population difference score is not equal to 0? So for my paired sample t-test, be straightforward. My test statistic is going to be my mean difference minus the expected difference under the null. What's the expected difference under the null? Got it. 0. Yep. So that goes away, right? So we got the mean difference or the standard error of the mean difference. Standard error of the mean difference is just going to be the standard deviation of the difference scores. We're going to square it in. Standard deviation of the mean difference is just the estimated standard error for the difference scores across assessments. If I were to take all possible samples that could be drawn from the population, I would look at those difference scores. How much would I expect those different scores to jump around across repeat replications? We can also think about the standard mean difference, the expected mean difference in scores within individual repeated across repeated assessments, assuming that the null is true, right? Assuming that if I measure you today and I measure you next week, and in the population, the actual difference between those is always going to be 0. Okay, so let's say how many hours a night you sleep, right? On average, if I measure you on week 1, how many hours you sleep, and next week, how many hours you sleep, probably hours of sleep is probably pretty stable for maybe not for graduates, but for most people, right? I'm not going to expect a difference across random sets, right? So certainly there will be differences in that sample difference mean, but on average, it's going to be equal to 0. So here we've got a very small data set where we've got 4 observations. We've got person A, person B, person C, person D. Here's the score at time 1. Here's the score at time 2. And this is the only thing we're working with, this vector of difference scores. Here's a difference of 4, 7, 5, -2. Here's the mean of my difference score. Here's the standard deviation of my difference score. This is what's going into the calculation of my test. Okay. So again, with my paired sample t-test, what I'm interested in is probability of obtaining a set of different scores with a mean difference of 3.5, assuming the my null model is true. Assuming that there is no difference in the population, what's the likelihood of me having a sample of 4 with a mean difference of 3.5? That's kind of what my test is doing. Yeah, quick throwback. Anything looking similar with this formula? Where do we see a similar formula set up to this?
Pretty similar, just with this, we're looking at the differences rather than the scores itself.
Pretty similar to what?
I'm not good with term, but like the initial t-test that we were doing, yeah.
All your paired sample t-test is just a single sample t-test with different scores. That's all it is, right? There's nothing special or fancy or magical about your paired sample t. It's just your single sample t, just with different scores. Okay, starts to become really, really important because the way you would approach your paired sample t test in terms of your screening and your interpretation is no different than your single sample t. It's just here we've got vector of scores at time 1 and time 2. But really, you're just testing, are these differences, is the mean of these different scores different than 0? That's all I'm doing with this. So conceptually, really helpful. Go through how many, Jack, how many sources of error do I have? So in my calculation, my independent, yeah, just one. It's one here, there. So again, this is what starts to make these tests very powerful. It's because before I basically cut my standard error in half because I'm only going to work with one source of error with this. Yeah.
Could you technically do the 2, but then you'd have 2 and that wouldn't be useful?
What's that now?
Could you technically do independent sample? Or
You-
no?
I mean, no, because sort of the assumption of the independent sample t-test is dependence, independence across your 2 samples. And yeah, these are for sure not independent because they're collected from the same person. And there would be no reason to actually do this because you would just be like shooting yourself in the foot in terms of power with this. Okay. So with your paired sample test, some assumptions: outcome variable is continuous, sampling distribution of the different scores of normal, the population. Informal assumptions is you don't have outliers. And then all of your auxiliary hypotheses that are always existing in the background. Your effect sizes for your paired sample tests. Here's where things start to get tricky because you got a lot of different things you could be doing with this. Okay. Mean difference score. This can be starting to become relevant. Again, if you're doing sort of treatment outcome, looking at underweighted people, looking at sort of pre and post, like are people gaining mass back, it starts to become important for health and things like that. Say, here's what how much things are increasing. Just the raw differences is a meaningful measure of effect in this situation. We also have Cohen's D, right? Cohen's D in general just says the mean of the different scores divided by a standard deviation estimate. The problem is that I don't know what standard deviation estimate to use here, right? So I can start to go through some different options. I can go through and calculate Cohen's D as my mean difference score over the square root of my average variance, okay? This would be taking my variance at time 1, variance at time 2, averaging those 2 things, and then taking the square root of that as my standardizer. Okay. Do I need to worry about pooling anything? No, why not, Finn?
Because we don't have, because we're just looking at the difference in scores rather than like the. Yeah.
So here, we are looking at sort of variance at time 1 scores, variance at time 2 scores, and we're just taking the average of that and taking the square root of that to get an estimate. Why don't we have to worry about pooling anything? Jack?
Because the sample size is the same.
It's the same people, right? There's no reason to. You could, if you want, you could go through and pool that, and it would be fine. You get the same thing. It's just a shortcut to just take the average of 2 variances because it's the same number of people ways. The thing to remember here, though, is always work with your variances. Don't take the average of your standard deviations. That'll give you a different number than taking the average of your variances and then taking the square root of that. Yeah. So this is, and this version here is basically, it's basically like a Hedges G for a repeated sample, right? So pretty straightforward. You can also use Glasses Delta. Okay. Glasses Delta is nice because if you have a true like baseline, then just look at sort of change relative to variability at baseline, right? So I go through and I do, and again, if I'm thinking about treatment study, here's your variability at baseline, and then how much change do we see in outcome relative to baseline. If you've got a good baseline, Glasses Delta can be helpful here. This is an opportunity or sort of a way to go through and calculate an effect size as an R squared. It's a measure of association. You'll see it sometimes, but I like, so if you're going to do an actual paired sample test and a means-based test, being able to interpret this as standard deviation units different starts to become useful here. One thing you want to be careful about, okay? You can sometimes use the standard deviation of different scores as a standardizer. The problem is if we're going through and looking at this, I can have wild variability here and wild variability here. and very little variability in your different scores. Has anybody ever done like psychophys types of work? A little bit like skin conductance or things along those lines. If you measure skin conductance across individuals varies widely, right? And so if I go through and I take people and I sort of have them sort of have some control baseline and measure their skin conductance, and then expose them to a stress or some manipulation and measure their skin conductance. At time one, I can have wild variability across individuals. Here, I can have wild variability across individuals. But my different scores here might be super tight because consistently, like our bodies are sort of limited. I can't sort of my skin conductance can't wildly jump around. If I start at a certain level, it can either go up or down sort of relative to the baseline. So you can have a massive standard deviation here, a massive standard deviation here, and then very small standard deviation here. So if I use the standard deviation of my different scores for the calculation of my effect size, what's this effect size going to be relative to that? It's going to be way higher, right? So we need to be careful in realizing the standard deviation of the different scores can start to look a lot different than what it would sort of relative to here. Okay. Here's another correction that you see sometimes. It's Cohen's d for a repeated measure. Here you're just taking regular Cohen's d and dividing it by a correction factor so that it accounts for the correlation between time points. This is an important kind of approach for power, but I don't know how you interpret that value. It loses all interpretability and it's going to be way higher than what you would get here. So know that these are things, but probably not for the purpose of interpretability, probably not as useful as some of these over here. Okay. Here I have an example for anger imagery. That I'll let you go through and walk through the videos to go through and do that. Again, screening interpretation is pretty straightforward just because it's basically a single sample t-test with different scores. Okay. So follow through those in your video. So this will catch up and sort of walk you through this piece of things. Want to finish up here with just talking about strengths and limitations of your paired sample T. Okay. Strengths, again, going to be included. It's a nice approach for measuring types of things that we're often interested in behavioral sciences. And it's more efficient resources. It results in more powerful tests, right? Which is all excellent. Okay. But we do have limitations, right? Influence of time-related factors. Okay. If I'm just going through and I'm measuring you today and you next week on things, there's all sorts of things as that time duration starts to increase. It starts to go through and sort of build in. And so I'm just sort of increasing compounds so that start to go through and change things. If there are things going on in the world that are sort of stressing us out or making us happy, all of those things are happening. I mean, it's so being accounted for by model. So there's some things we need to be thinking about in terms of how long do we want to go through and make that window of assessment? How's that going to impact our tests? Things along these lines. Let's have the influence of practice effects, right? If I'm going through and seeing how well do you do on this one thing, and then what happens if I go through and try and give you the same test sort of down the road, right? Those of you in Tara's assessment class, don't know if you got to this point yet, but do you go through and give someone an IQ test and then give the same one to them again 3 weeks later? Nope, you sure don't, because there's going to be practice effects going on there, right? And so you might see a huge increase. It's because I already had some practice at it the first time around, right? So you want to make sure as you're thinking about these designs, are there practice effects? Are there reasons that sort of if I do this once, can I do it again, or do people kind of already know the shtick and then they're already sort of it's going to impact how they go through and sort of perform on the next one. Also have an issue with order effects. Okay. This is if I go through and I do this, then it's going to go through and necessarily influence the next time I go through and do this. This is different than practice effects. This is let's say, again, I'll use a clinical example. I go through and I run you all, because I'm running you through a CBT protocol for social anxiety. Because you're all socially anxious. I run you through my study where I'm giving you CBT for social anxiety, give you a bunch of skills, you're feeling better, you're doing some exposure, you're kind of out there, putting yourself out there. I'm like, awesome, cool. Forget all of that. I'm gonna give you sort of psychodynamic therapy or interpersonal therapy for stuff. So don't do any of the thing I was telling you to do before. Now do this other thing. Is that gonna work? No, because you're gonna remember all the stuff that you did before, and like by definition. Or if I go through and I give you some interpersonal dynamic therapy at first and then do the other thing, like I can't unlearn the thing that I already learned. And so then that makes it not feasible for me to now go through and learn a whole new thing without that other thing stuff, right? So if we have the potential for order effects, they can start to complicate how you can actually go through it. And so actually these types of designs. So the code from, I didn't have a picture of Zach, so I sort of created a young sort of Zach Williamson picture here. Like, Zach, why do we like repeating? Or repeating those pretty damn slow. Like that's a true statement. Right? These are going to be different designs that are going to be critical to theses, dissertations, things along those lines. There's some additional wrinkles and things you need to think about. But anytime you can implement a repeated measures design into your study, do so, because it's going to just make it that much stronger there. We fight with low power always, almost always in our research. This is a really, really nice way to increase your power. If you want to find subtle stuff, you incorporate a repeated measures design, you're much, much likelier to find what you're looking for if you can sort of use this. So know these, get familiar with these, get comfortable with these, because these are a really, really excellent tool. All right. So just to kind of summarize this, our single sample T, here we're comparing the mean of a continuous variable obtained from a single sample to some known population or reference mean when my variance is unknown. Population variance is unknown. Okay. We're testing that our null hypothesis has some sort of population value, some reference point, right? So if you just got one sample and you're testing against some reference point, either because it's a population value that you know, or it's just some relevant sort of thing to something you're interested in, you're looking at your single sample T. Okay. Independent sample T, this is easy. We're just looking at two different groups and seeing whether or not the population, wanting to test whether or not the population means across these two groups are equal to one another. Okay. In our paired sample, again, we're looking at change on a continuous outcome collected across two different occasions. Okay. Within the same group of people, asterisks, because it's the same group of people unless you've got a matched design. If it's a matched design, then you're still going to use your paired sample approach. You're just looking at the difference between your target person and that matched person and using that as your difference scores as opposed to the same person measured across multiple occasions. Okay. And then again, you're testing the tests that meet different scores of the population. All right. So again, take home points, make sure to go through and look at those as kind of as a summary. We got general appendices sort of back here, but you already have those in the handouts. All right. So here's what we're going to do. We will have our current problem set due on Friday, right? So go through and knock that out. Okay. Then what we're going to go through and do is our next problem set, our t-test one, is going to be due sort of the following Friday. Okay, these are going to get stacked together. Okay, starts to become really, really important that you get a head start on this and start looking at it. Okay, but what we're going to do for class next time is we'll devote half the class to just kind of like lab and going through and sort of working through stuff. Okay. That's not going to give you time to do the whole set. But if you get started on it and start working on stuff, what we'll do is take all the sort of time that I'm having to watch videos and stuff like that, go through, watch those, and what we can do for the start of the class next week is have you working on those sets, work together, so to ask them questions. We'll just have that first, say, hour and a half time to just go through and just work on sort of working through these sets, okay? That'll give you some time to go through and get answers, questions answered. If someone has a question, I can go through and field it to everybody. So we'll use that first half of lab time for some questions, and then sort of the stuff on effect size, intervals or not, effect size, those stuff. Okay. Questions about sort of the plan. Then what I'm gonna do is I'm also gonna go through and take a look and see, is what we also need to do is you need to get, Helene and I, your, problem sets. Then we need to turn those around, score those, get them back to you, that you have time to go through and look through them, which doesn't actually take a whole ton of time, but does start to, I mean, things start to get sort of packed in a little bit on all with stuff. So I'm gonna go through and take a look and see, does anybody have, I guess, and you don't have to sort of out yourself right now, so to get jumped by your classmates, but if we were to push, sort of the mid-semester exam back a week, would that create problems for anybody? Okay.
I'm nervous either way, so either get it over with or get extra time.
Yeah, so I just, sort of the in-class exams are nerve-wracking. They're kinder than having you give you a take home, even though, because if I do that, then it will be your life for as long as I let you go through and do it, and you spend far more time sort of actually doing. And I can expect far more from you if you have time to go through and do things. If you're coming here and I'm asking you to produce knowledge in class for a set period, now, I'm not gonna like rip your exam away from you after 3 hours. I'll sit here for as long as you need to feel comfortable to go through and answer things, but it will not take you. I'm not designing this as a 3-hour exam. People will take 3 hours, and sometimes they're hour long, just because it's a sort of a, and that's your process, and I'm fine with that, right? But I'm not writing this to be a 3-hour exam and stuff, right? So, and you don't have to memorize any formula or anything like that. I'll give you a sheet that has formula for anything that you'll need. You'll need to be able to go through and take a look and know back, oh, that's for an independent exam t-test, or that's for this and that, right? We're not gonna have you do any SPSS or anything along those lines with this. I may have you interpret output or things along those lines. So you wanna make sure that you're sort of up to speed with that, okay? Again, sort of the in-class exam is just sort of the only way I've got, because I do want you working together on problem sets and learning from one another and sort of bouncing ideas off one another. So this is kind of the one opportunity to say like, okay, do you have just, you on your own have an understanding of kind of what's going on. And that exam, if you go through and look through your problem sets, you got stuff on the problem sets, you're comfortable with that. You look through the stuff on your, through the lecture slides, you're feeling pretty comfortable with that. You go through and look at your readings, feel like you got a handle on that. You're pretty good to go, okay? But I'll go through, take a look, talk with Helena, just kind of see where we're at with stuff, and then kind of let you know kind of where we're at. So, yeah. All right, cool. Questions for me? All right, if they come up, let me know. Thank you so much. We kind of went through this, so the last piece, a little bit quickly, but go through, watch those videos, sort of make sure that you're comfortable sort of going through, and the SPSS stuff is actually pretty straightforward. Just making sure that with that upcoming set, you'll turn in your electronic copy, okay, of your problem set, and then also you'll submit to me and Helena your syntax file, and then your SPSS data file that you ran the syntax on. The idea is that I should be able to go through, if I see something wonky in your output, I should be able to go through and run the syntax file that you gave me on the data set that you gave me and reproduce the stuff that you're reporting in the set. That helps me. If here's something's off base, I can go through and just look at the syntax file and be like, oh, you got those switched around. So those lines makes it easy for me to go through and diagnose and check. The other thing that is useful is if you just go through and you run a t-test, don't print it, don't give me the whole output, because that's not useful, because then you're just like projecting sort of things that SPSS gave you onto a page, and I don't know that you understand sort of what's going on. But going through and like taking screenshots of tables and just posting those in there is a much more efficient way for me to go through and take a look and see if you got what you should have, as opposed to you trying to hand type in figures. Because then I don't know if you actually just mistype something or something along those lines. So just want you to get good at sort of posting images in there and sort of like arranging them into your set in ways that are sort of easy for us to go through and check on stuff. So if you have questions, let me know. And thanks, folks.
Thank you.
Thank you.
That's due on this Friday.
Yeah.